In a closed container, molecules with relatively higher kinetic energy escape the liquid surface into the vapor phase, and number of liquid molecules from the vapor phase strike the liquid surface and are retained in the liquid phase. It gives rise to a constant vapor pressure because of an equilibrium in which the number of molecules leaving the liquid equals the number returning to liquid from the vapor. We say that the system has reached equilibrium state at this stage. However, this is not static equilibrium, and there is a lot of activity at the boundary between the liquid and the vapor. Thus, at equilibrium, the rate of evaporation is equal to the rate of condensation. It may be represented by H2O, L, H2O, VAP. The double half arrows indicate that the processes in both the directions are going on simultaneously. The mixture of reactants and products in the equilibrium state is called an equilibrium mixture. Equilibrium can be established for both physical processes and chemical reactions. The reaction may be fast or slow depending on the experimental conditions and the nature of the reactants. When the reactants in a closed vessel at a particular temperature react to give products, the concentrations of the reactants keep on decreasing, while those of products keep on increasing for some time, after which there is no change in the concentrations of either of the reactants or products. This stage of the system is the dynamic equilibrium, and the rates of the forward and after studying this unit you will be able to identify dynamic nature of equilibrium involved in physical and cation on concentration of the electrolyte and that of the common ion, describe pH scale for representing hydrogen ion concentration, explain ionization of water and its dual role as acid and base, describe ionic product, Kw, and pKw for water, appreciate use of buffer solutions, calculate solubility product constant. 2019-20. 193 Equilibrium reverse reactions become equal. It is due to this dynamic equilibrium stage that there is no change in the concentrations of various species in the reaction mixture. Based on the extent to which the reactions proceed to reach the state of chemical equilibrium, these may be classified in three groups. I. The reactions that proceed nearly to completion and only negligible concentrations of the reactants are left. In some cases, it may not be even possible to detect these experimentally. 2. The reactions in which only small amounts of products are formed and most of the reactants remain unchanged at equilibrium stage. 3. The reactions in which the concentrations of the reactants and products are comparable, when the system is in equilibrium. The extent of a reaction in equilibrium varies with the experimental conditions such as concentrations of reactants, temperature, etc. Optimization of the operational conditions is very important in industry and laboratory so that equilibrium is favorable in the direction of the desired product. Some important aspects of equilibrium involving physical and chemical processes are dealt in this unit, along with the equilibrium involving ions in aqueous solutions, which is called as Ionic Equilibrium. 7.1 Equilibrium in physical processes. The characteristics of system at equilibrium are better understood if we examine some physical processes. The most familiar examples are phase transformation processes, e.g., solid-liquid, liquid-gas, solid-gas. 7th January 2001 Solid-liquid equilibrium. Ice and water kept in a perfectly insulated thermos flask. No exchange of heat between its contents and the surroundings, at 273 K and the atmospheric pressure are in equilibrium state, and the system shows interesting characteristic features. We observe that the mass of ice and water do not change with time and the temperature remains constant. However, the equilibrium is not static. The intense activity can be noticed at the boundary between ice and water. Molecules from the liquid water collide against ice and adhere to it, and some molecules of ice escape into liquid phase. There is no change of mass of ice and water, as the rates of transfer of molecules from ice into water and of reverse transfer from water into ice are equal at atmospheric pressure and 273 K. It is obvious that ice and water are in equilibrium only at particular temperature and pressure. For any pure substance at atmospheric pressure, the temperature at which the solid and liquid phases are at equilibrium is called the normal melting point or normal freezing point of the substance. The system here is in dynamic equilibrium, and we can infer the following: I. Both the opposing processes occur simultaneously. 2. Both the processes occur at the same rate so that the amount of ice and water remains constant. 7th January 2002 Liquid-vapor equilibrium. This equilibrium can be better understood if we consider the example of a transparent box carrying a U-tube with mercury, manometer, drying agent like anhydrous calcium chloride, or phosphorus pentaoxide, is placed for a few hours in the box. After removing the drying agent by tilting the box on one side, a watch glass, or petri dish, containing water is quickly placed inside the box. It will be observed that the mercury level in the right limb of the manometer slowly increases and finally attains a constant value, that is, the pressure inside the box increases and reaches a constant value. Also the volume of water in the watch glass decreases. Fig 7.1. Initially there was no water vapor, or very less, inside the box. As water evaporated, the pressure in the box increased due to addition of water. 2019 to 20. 194 chemistry molecules into the gaseous phase inside the box. The rate of evaporation is constant. However, the rate of increase in pressure decreases with time due to condensation of vapor into water. Finally, it leads to an equilibrium condition when there is no net evaporation. This implies that the number of water molecules from the gaseous state into the liquid state also increases till the equilibrium is attained, i.e., rate of evaporation is equal to rate of condensation H2O, L, H2O, VAP. At equilibrium, the pressure exerted by the water molecules at a given temperature remains constant and is called the equilibrium vapor pressure of water, or just vapor pressure of water. Vapor pressure of water increases with temperature. If the above experiment is repeated with methyl alcohol, acetone and ether, it is observed that different liquids have different equilibrium vapor pressures at the same temperature, and the liquid which has a higher vapor pressure is more volatile and has a lower boiling point. If we expose 3 watch glasses containing separately 1 ml each of acetone, ethyl alcohol, and water to atmosphere and repeat the experiment with different volumes of the liquids in a warmer room, it is observed that in all such cases the liquid eventually disappears and the time taken for complete evaporation depends on I. The nature of the liquid, 2. The amount of the liquid, and 3. The temperature. When the watch glass is open to the atmosphere, the rate of evaporation remains constant but the molecules are dispersed into large volume of the room. As a consequence, the rate of condensation from vapor to liquid state is much less than the rate of evaporation. These are open systems and it is not possible to reach equilibrium in an open system. Water and water vapor are in equilibrium position at atmospheric pressure, 1.013 bar, and at 100 degrees Celsius in a closed vessel. The boiling point of water is 100 degrees Celsius at 1.013 bar pressure. For any pure liquid at 1 atmospheric pressure, 1.013 bar, the temperature at which the liquid and vapors are at equilibrium is called normal boiling point of the liquid. Boiling point of the liquid depends on the atmospheric pressure. It depends on the altitude of the place. At high altitude the boiling point decreases. 7th January 2003 Solid vapor equilibrium. Let us now consider the systems where solids sublime to vapor phase. If we place solid iodine in a closed vessel, after some time the vessel gets filled up with violet vapor and the intensity of color increases with time. After certain time the intensity of color becomes constant and at this stage equilibrium is attained. Hence solid iodine sublimes to give iodine vapor and the iodine vapor condenses to give solid iodine. The equilibrium can be represented as I2, solid, I2, vapor. Other examples showing this kind of equilibrium are CAM4, solid, CAM4, vapor, NH4Cl, solid, NH4Cl, vapor. Fig. 7.1 Measuring equilibrium vapor pressure of water at a constant temperature 2019-20. Equilibrium 7th January 2004 Equilibrium involving dissolution of solid or gases in liquids. Solids in liquids. We know from our experience that we can dissolve only a limited amount of salt or sugar in a given amount of water at room temperature. If we make a thick sugar syrup solution by dissolving sugar at a higher temperature, sugar crystals separate out if we cool the syrup to the room temperature. We call it a saturated solution when no more of solute can be dissolved in it at a given temperature. The concentration of the solute in a saturated solution depends upon the temperature. In a saturated solution, a dynamic equilibrium exists between the solute molecules in the solid state and in the solution, sugar, solution, sugar, solid, and the rate of dissolution of sugar is equal to rate of crystallization of sugar. Equality of the two rates and dynamic nature of equilibrium has been confirmed with the help of radioactive sugar. If we drop some radioactive sugar into saturated solution of non-radioactive sugar, then after some time radioactivity is observed both in the solution and in the solid sugar. Initially there were no radioactive sugar molecules in the solution, but due to dynamic nature of equilibrium, there is exchange between the radioactive and non-radioactive sugar molecules between the two phases. The ratio of the radioactive to non-radioactive molecules in the solution increases till it attains a constant value. Gases in liquids. When a soda water bottle is opened, some of the carbon dioxide gas dissolved in it fizzes out rapidly. The phenomenon arises due to difference in solubility of carbon dioxide at different pressures. There is equilibrium between the molecules in the gaseous state and the molecules dissolved in the liquid under pressure, i.e., CO2, gas, CO2, in solution. This equilibrium is governed by Henry's law, which states that the mass of a gas dissolved in a given mass of a solvent at any temperature is proportional to the pressure of the gas above the solvent. This amount decreases with increase of temperature. The soda water bottle is sealed under pressure of gas when its solubility in water is high. As soon as the bottle is opened, some of the dissolved carbon dioxide gas escapes to reach a new equilibrium condition required for the lower pressure, namely its partial pressure in the atmosphere. This is how the soda water in bottle, when left open to the air for some time, turns flat. It can be generalized that I, for solid-liquid equilibrium, there is only one temperature, melting point, at 1 atm, 1.013 bar, at which the two phases can coexist. If there is no exchange of heat with the surroundings, the mass of the two phases remains constant. 2. For liquid-vapor equilibrium, the vapor pressure is constant at a given temperature. 3. For dissolution of solids in liquids, the solubility is constant at a given temperature. 4. For dissolution of gases in liquids, the concentration of a gas in liquid is proportional to the pressure, concentration, of the gas over the liquid. These observations are summarized in Table 7.1. Liquid vapor pH 2 constant at given H2O, L, H2O, G. Temperature solid liquid melting point is fixed at H2O, S, H2O, L. Constant pressure solute, S. Solute concentration of solute, solution, in solution is constant sugar, S. Sugar at a given temperature, solution, gas, G, gas, AC, gas, AC, gas, G, is constant at a given temperature CO2, G, CO2, AC, CO2, AC, CO2, G, is constant at a given temperature. Table 7.1. Some features of physical equilibria process conclusion 2019-20. 196 Chemistry 7th January 2005 General characteristics of equilibria involving physical processes. For the physical processes discussed above, following characteristics are common to the system at equilibrium. I. Equilibrium is possible only in a closed system at a given temperature. 2. Both the opposing processes occur at the same rate and there is a dynamic but stable condition. 3. All measurable properties of the system remain constant. 4. When equilibrium is attained for a physical process, it is characterized by constant value of one of its parameters at a given temperature. Table 7.1 lists such quantities. V. The magnitude of such quantities at any stage indicates the extent to which the physical process has proceeded before reaching equilibrium. 7.2 Equilibrium in chemical processes. Dynamic equilibrium analogous to the physical system's chemical reactions also attain a state of equilibrium. These reactions can occur both in forward and backward directions. When the rates of the forward and reverse reactions become equal, the concentrations of the reactants and the products remain constant. This is the stage of chemical equilibrium. This equilibrium is dynamic in nature as it consists of a forward reaction in which the reactants give product, S, and reverse reaction in which product, S, gives the original reactants. For a better comprehension, let us consider a general case of a reversible reaction, A plus B C plus D. With passage of time, there is accumulation of the products C and D and depletion of the reactants A and B. Fig. 7.2. This leads to a decrease in the rate of forward reaction and an increase in the rate of the reverse reaction. Fig. 7.2 Attainment of chemical equilibrium. Eventually, the two reactions occur at the same rate and the system reaches a state of equilibrium. Similarly, the reaction can reach the state of equilibrium even if we start with only C and D, that is, no A and B being present initially, as the equilibrium can be reached from either direction. The dynamic nature of chemical equilibrium can be demonstrated in the synthesis of ammonia by Haber's process. In a series of experiments, Haber started with known amounts of dinitrogen and the hydrogen maintained at high temperature and pressure and at regular intervals determined the amount of ammonia present. He was successful in determining also the concentration of unreacted dihydrogen and dinitrogen. Fig. 7.4, page 191, shows that after a certain time the composition of the mixture remains the same even though some of the reactants are still present. This constancy in composition indicates that the reaction has reached equilibrium. In order to understand the dynamic nature of the reaction, synthesis of ammonia is carried out with exactly the same starting conditions, of partial pressure and temperature, but using D2, deuterium, in place of H2. The reaction mixtures starting either with H2 or D2 reach equilibrium with the same composition, except that D2 and ND3 are present instead of H2 and NH3. After equilibrium is attained, these two mixtures 2019-20. 197 Equilibrium. Dynamic equilibrium. A student's activity equilibrium, whether in a physical or in a chemical system, is always of dynamic nature. This can be demonstrated by the use of radioactive isotopes. This is not feasible in a school laboratory. However, this concept can be easily comprehended by performing the following activity. The activity can be performed in a group of 5 or 6 students. Take two 100 ml measuring cylinders, marked as 1 and 2, and two glass tubes each of 30 cm length. Diameter of the tubes may be same or different in the range of 3 to 5 mm. Fill nearly half of the measuring cylinder 1 with colored water. For this purpose add a crystal of potassium permanganate to water, and keep second cylinder, number 2, empty. Put one tube in cylinder 1 and second in cylinder 2. Immerse one tube in cylinder 1, close its upper tip with a finger and transfer the colored water contained in its lower portion to cylinder 2. Using second tube, kept in second cylinder, transfer the colored water in a similar manner from cylinder 2 to cylinder 1. In this way keep on transferring colored water using the two glass tubes from cylinder 1 to 2 and from 2 to 1 till you notice that the level of colored water in both the cylinders becomes constant. If you continue intertransferring colored solution between the cylinders, there will not be any further change in the levels of colored water in two cylinders. If we take analogy of level of colored water with concentration of reactants and products in the two cylinders, we can say the process of transfer, which continues even after the constancy of level, is indicative of dynamic nature of the process. If we repeat the experiment taking two tubes of different diameters, we find that at equilibrium the level of colored water in two cylinders is different. How far diameters are responsible for change in levels in two cylinders? Empty cylinder, 2, is an indicator of no product in it at the beginning. Fig. 7.3 demonstrating dynamic nature of equilibrium. A. Initial stage. B. Final stage after the equilibrium is attained. 2019-20. 198 Chemistry 2NH3, G, N2, G, plus 3H2, G. Similarly, let us consider the reaction H2, G, plus I2, G, 2 high, G. If we start with equal initial concentration of H2 and I2, the reaction proceeds in the forward direction and the concentration of H2 and I2 decreases while that of high increases, until all of these become constant at equilibrium. Fig. 7.5. We can also start with high alone and make the reaction to proceed in the reverse direction. The concentration of high will decrease and concentration of H2 and I2 will increase until they all become constant when equilibrium is reached. Fig. 7.5. If total number of H and I atoms are same in a given volume, the same equilibrium mixture is obtained whether we start it from pure reactants or pure product. H2N2NH3 and D2N2ND3 are mixed together and left for a while. Later, when this mixture is analyzed, it is found that the concentration of ammonia is just the same as before. However, when this mixture is analyzed by a mass spectrometer, it is found that ammonia and all deuterium-containing forms of ammonia, NH3, NH2D, NHD2 and ND3, and the hydrogen and its deuterated forms, H2HD and D2, are present. Thus one can conclude that scrambling of H and D atoms in the molecules must result from a continuation of the forward and reverse reactions in the mixture. If the reaction had simply stopped when they reached equilibrium, then there would have been no mixing of isotopes in this way. Use of isotope, deuterium, in the formation of ammonia clearly indicates that chemical reactions reach a state of dynamic equilibrium in which the rates of forward and reverse reactions are equal and there is no net change in composition. Equilibrium can be attained from both sides, whether we start reaction by taking H2, G, and N2, G, and get NH3, G, or by taking NH3, G, and decomposing it into N2, G, and H2, G, N2, G, plus 3H2, G, 2NH3, G. Fig 7.4 depiction of equilibrium for the reaction. Fig. 7.5 Chemical equilibrium in the reaction H2, G, plus I2, G, 2 high, G, can be attained from either direction. 7.3 Law of chemical equilibrium and equilibrium constant. A mixture of reactants and products in the equilibrium state is called an equilibrium mixture. In this section we shall address a number of important questions about the composition of equilibrium mixtures. What is the relationship between the concentrations of reactants and products in an equilibrium mixture? How can we determine equilibrium concentrations from initial concentrations? NGHG NHG 22332 plus 2019 to 20. 199 Equilibrium. What factors can be exploited to alter the composition of an equilibrium mixture? The last question in particular is important when choosing conditions for synthesis of industrial chemicals such as H2NH3, CaO, etc. To answer these questions, let us consider a general reversible reaction, A plus B C plus D, where A and B are the reactants, C and D are the products in the balanced chemical equation. On the basis of experimental studies of many reversible reactions, the Norwegian chemists Cato Maximilian Guldberg and Peter Waag proposed in 1864 that the concentrations in an equilibrium mixture are related by the following equilibrium equation: Kc is equal to CdAb 7.1, where Kc is the equilibrium constant and the expression on the right side is called the equilibrium constant expression. The equilibrium equation is also known as the law of mass action because in the early days of chemistry, concentration was called active mass. In order to appreciate their work better, let us consider reaction between gaseous H2 and I2 carried out in a sealed vessel at 731 K. H2, G, plus I2, G, 2 high, G, 1 mol 2 mol. 6 sets of experiments with varying initial conditions were performed, starting with only gaseous H2 and I2 in a sealed reaction vessel in first 4 experiments, 1, 2, 3 and 4, and only high in other 2 experiments, 5 and 6. Experiment 1, 2, 3 and 4 were performed taking different concentrations of H2 and or I2, and with time it was observed that intensity of the purple color remained constant and equilibrium was attained. Similarly, for experiments 5 and 6, the equilibrium was attained from the opposite direction. Data obtained from all 6 sets of experiments are given in Table 7.2. It is evident from the experiments 1, 2, 3 and 4 that number of moles of the hydrogen reacted is equal to number of moles of iodine reacted is equal to a half number of moles of high formed. Also, experiments 5 and 6 indicate that H2, G, Ec is equal to I2, G, Ec. Knowing the above facts, in order to establish a relationship between concentrations of the reactants and products, several combinations can be tried. Let us consider the simple expression high G, Ec, H2, G, Ec, I2, G, Ec. It can be seen from Table 7.3 that if we put the equilibrium concentrations of the reactants and products, the above expression Table 7.2 initial and equilibrium concentrations of H2, I2 and high 2019 to 20. (200) Chemistry is far from constant. However, if we consider the expression high G, 2 Ec, H2, G, Ec, I2, G, Ec, we find that this expression gives constant value, as shown in Table 7.3, in all the 6 cases. It can be seen that in this expression the power of the concentration for reactants and products are actually the stoichiometric coefficients in the equation for the chemical reaction. Thus, for the reaction H2, G, plus I2, G, 2 high, G, following equation 7.1, the equilibrium constant Kc is written as Kc is equal to high G, Ec 2, H2, G, Ec, I2, G, Ec. 7.2. Generally the subscript Ec used for equilibrium is omitted from the concentration terms. It is taken for granted that the concentrations in the expression for Kc are equilibrium values. We, therefore, write Kc is equal to high G, 2, H2, G, I2, G. 7.3. The subscript C indicates that Kc is expressed in concentrations of mol L1. At a given temperature, the product of concentrations of the reaction products raised to the respective stoichiometric coefficient in the balanced chemical equation divided by the product of concentrations of the reactants raised to their individual stoichiometric coefficients has a constant value. This is known as the equilibrium law or law of chemical equilibrium. The equilibrium constant for a general reaction AA plus B B C C plus D D is expressed as Kc is equal to C, C, D, D, A, B, B. 7.4, where A, B, C, and D are the equilibrium concentrations of the reactants and products. Equilibrium constant for the reaction 4NH3, G, plus 5O2, G, 4NO, G, plus 6H2O, G, is written as Kc is equal to NO, 4, H2O, 6, NH3, 4, O2. 5 molar concentration of different species is indicated by enclosing these in square bracket, and, as mentioned above, it is implied that these are equilibrium concentrations. While writing expression for equilibrium constant, symbol for phases S, L, G are generally ignored. Let us write equilibrium constant for the reaction H2, G, plus I2, G, 2 high, G, 7.5, as Kc is equal to high, 2, H2, I2 is equal to X 7.6. The equilibrium constant for the reverse reaction 2 high G H2 G plus I2 G at the same temperature is K C is equal to H2 I2 high 2 is equal to 1 X is equal to 1 Kc 7.7. Thus K C is equal to 1 Kc 7.8. Equilibrium constant for the reverse reaction is the inverse of the equilibrium constant for the reaction in the forward direction. If we change the stoichiometric coefficients in a chemical equation by multiplying throughout by a factor, then we must make sure that the expression for equilibrium constant also reflects that change. For example, if the reaction 7.5 is written as a half H2 G plus a half I2 G high G 7.9, the equilibrium constant for the above reaction is given by Kc is equal to high H2 12 I2 12 is equal to high 2 H2 I2 12 is equal to X 12 is equal to Kc 12 7.10. On multiplying the equation 7.5 by n, we get table 7.3 expression involving the equilibrium concentration of reactants H2 G plus I2 G 2 high G 2019 to 20. Equilibrium NH2 G plus Ni2 G D2NHI G 7.11. Therefore, equilibrium constant for the reaction is equal to Kcn. These findings are summarized in table 7.4. It should be noted that because the equilibrium constants Kc and Kc have different numerical values, it is important to specify the form of the balanced chemical equation when quoting the value of an equilibrium constant. 800 K. What will be Kc for the reaction N2 G plus O2 G 2 No G? Solution for the reaction equilibrium constant Kc can be written as Kc is equal to No is equal to 2.810 m3 times 222-2333010 4th February 2010 No is equal to 0.6227.4 homogeneous equilibria. In a homogeneous system, all the reactants and products are in the same phase. For example, in the gaseous reaction, N2 G plus 3H2 G 2NH3 G, reactants and products are in the homogeneous phase. Similarly, for the reactions CH3 Cook 2H5 AC plus H2O L CH3 Cu AC plus C2H5O AC and Fe3 plus AC plus SCN AC Fe SCN 2 plus AC, all the reactants and products are in homogeneous solution phase. We shall now consider equilibrium constant for some homogeneous reactions. 7th April 2001 Equilibrium constant in gaseous systems. So far we have expressed equilibrium constant of the reactions in terms of molar concentration of the reactants and products, and used symbol Kc for it. For reactions involving gases, however, it is usually more convenient to express the equilibrium constant in terms of partial pressure. The ideal gas equation is written as PV is equal to nRT NVT is equal to R. Here, P is the pressure in Pa, N is the number of moles of the gas, V is the volume in M3 and T is the temperature in Kelvin. Problem 7.1. The following concentrations were obtained for the formation of NH3 from N2 and H2 at equilibrium at 500 K. N2 is equal to 1.5 times 10 to m. H2 is equal to 3.0 times 10 to m and NH3 is equal to 1.2 times 10 to m. Calculate equilibrium constant. Solution: the equilibrium constant for the reaction N2G plus 3H2G 2NH3G can be written as Kc is equal to NHG NGHG 3222322 1st February 2010 1510 times 330103 times is equal to 0.106 times 104 is equal to 1.06 times 103. Problem 7.2. At equilibrium, the concentrations of N2 is equal to 3.0 times 10�3 m, O2 is equal to 4.2 times 10�3 m, and NO is equal to 2.8 times 10�3 m in a sealed vessel. At table 7.4, relations between equilibrium constants for a general reaction and its multiples. Chemical equation: equilibrium constant AA plus BBCC plus DDKCCC plus DDAA plus BBK. C is equal to 1 Kc. Na A plus NBB NCC plus NDDK. C is equal to KCN 2019 to 20. 202. Chemistry. Therefore, NV is concentration expressed in mol M3 if concentration C is in mol L or mol dm3, and P is in bar, then P is equal to CRT. We can also write P is equal to gas RT. Here, R is equal to 0.0831 bar liter mol K. At constant temperature, the pressure of the gas is proportional to its concentration, i.e., P gas. For reaction in equilibrium H2G plus I2G 2 high G, we can write either Kc high G Hg it is equal to 222 or Kppc high is equal to 222 7.12. Further, since PTP high I high Gr is equal to 22222 is equal to IgRHGRHTPT, therefore KPPPTTP is equal to high GGG 22222 is equal to high RHR. IRRT is equal to high GGG is equal to 222 Kc 7.13. In this example, Kp is equal to Kc, i.e., both equilibrium constants are equal. However, this is not always the case. For example, in reaction N2G plus 3H2G 2NH3G, Kp is equal to PPP NH32223 is equal to NHGR 3322223 at T is equal to NHGR 33 February 1922 to THKTC or KKTPC is equal to R2 7.14. Similarly, for a general reaction AA plus BBCC plus DDKPPPPTTPCCDDAABBCDCDABAB is equal to plus CDRABR is equal to plus CDABR CDABCDABT is equal to CDABRR CDABCTKTNN 7.15, where N is equal to number of moles of gaseous products, number of moles of gaseous reactants. In the balanced chemical equation, it is necessary that while calculating the value of Kp, pressure should be expressed in bar because standard state for pressure is 1 bar. We know from Unit 1 that 1 Pascal Pa is equal to 1 nm2, and 1 bar is equal to 105 Pa. Kp values for a few selected reactions at different temperatures are given in Table 7.5. Table 7.5 Equilibrium constants. Kp for a few selected reactions. Problem 7.3 PCl5, PCl3 and Cl2 are at equilibrium at 500 K and having concentration 1.59 m PCl3, 1.59 m Cl2 and 1.41 m PCl5 2019-20. 203 Equilibrium. Calculate Kc for the reaction PCl5 PCl3 plus Cl2 solution. The equilibrium constant Kc for the above reaction can be written as Kc PCl Cl PCl is equal to 32 520 159 141 179. Problem 7.4. The value of Kc is equal to 4.24 at 800 K for the reaction Co G plus H2O G Co2 G plus H2 G. Calculate equilibrium concentrations of Co2, H2 Co and H2O at 800 K. If only Co and H2O are present initially at concentrations of 0.10 m each. Solution for the reaction Co G plus H2O G Co2 G plus H2 G. Initial concentration 0.1 m 0.1 m 00. Let x mole per liter of each of the product be formed. At equilibrium 0.1 x m 0.1 x m, where x is the amount of Co2 and H2 at equilibrium. Hence, equilibrium constant can be written as Kc is equal to x2, 0.1 x, 2 is equal to 4.24 x2 is equal to 4.24, 0.01 plus x2 dash 0.2 x. x2 is equal to 0.0424 plus 4.24 x2 dash 0.848 x3.24 x2 0.848 x plus 0.0424 is equal to 0. A is equal to 3.24, B is equal to 0.848, C is equal to 0.0424. For quadratic equation x2 plus bx plus c is equal to 0, x bbca is equal to plus or minus 242x is equal to 0.848 plus or minus 0.848, 24, 3.24, 0.0424, 3.24 times 2, x is equal to 0.848 plus or minus 0.4118, 6.48 x1 is equal to 0.848 0.4118, 6.48 is equal to 0.067 x2 is equal to 0.848 plus 0.4118, 6.48 is equal to 0.194. The value 0.194 should be neglected because it will give concentration of the reactant which is more than initial concentration. Hence the equilibrium concentrations are Co2 is equal to H2 is equal to X is equal to 0.067 m, Co is equal to H2O is equal to 0.10 0.067 is equal to 0.033 m. Problem 7.5 for the equilibrium 2NOCl G 2NO G plus Cl2 G. The value of the equilibrium constant Kc is 3.75 times 10⁶ at 1069 K. Calculate the Kp for the reaction at this temperature. Solution. We know that Kp is equal to Kc RT. N for the above reaction, N is equal to 2 plus 1, 2 is equal to 1. Kp is equal to 3.75 times 10⁶, 0.0831 times 1069. Kp is equal to 0.0337.5. Heterogeneous equilibria. Equilibrium in a system having more than one phase is called heterogeneous equilibrium. The equilibrium between water vapor and liquid water in a closed container is an example of heterogeneous equilibrium. H2O, L, H2O, G. In this example, there is a gas phase and a liquid phase. In the same way, equilibrium between a solid and its saturated solution, CaO2, S plus, Ac, Ca2 plus, Ac, plus 2O, Ac, is a heterogeneous equilibrium. Heterogeneous equilibria often involve pure solids or liquids. We can simplify equilibrium expressions for the heterogeneous equilibria involving a pure liquid or a pure solid, as the molar concentration of a pure solid or liquid is constant, i.e., independent of the amount present. In other words, if a substance, X, is involved, then X, S, and X, L, are constant, whatever the amount of X is taken. Contrary 2019 to 20. (204) Chemistry to this, X, G, and X, Ac, will vary as the amount of X in a given volume varies. Let us take thermal dissociation of calcium carbonate, which is an interesting and important example of heterogeneous chemical equilibrium. CaCO3, S, CaO, S, plus CO2, G, 7.16. On the basis of the stoichiometric equation, we can write Kc is equal to CaOS Co G CaCOS 23 since CaCO3, S, and CaO, S, are both constant, therefore modified equilibrium constant for the thermal decomposition of calcium carbonate will be Kc is equal to CO2, G, 7.17, or Kp is equal to PCO2, 7.18. This shows that at a particular temperature, there is a constant concentration or pressure of CO2 in equilibrium with CaO, S, and CaCO3, S. Experimentally, it has been found that at 1100 K, the pressure of CO2 in equilibrium with CaCO3, S, and CaO, S, is 2.0 times 105 Pa. Therefore, equilibrium constant at 1100 K for the above reaction is Kp is equal to PCO2 is equal to 2 times 105 Pa. 105 Pa is equal to 2.00. Similarly, in the equilibrium between nickel, carbon monoxide and nickel carbonyl, used in the purification of nickel, Ni, S, plus 4 Co, G, Ni, Co, 4, G. The equilibrium constant is written as Kc is equal to Ni Co 4. It must be remembered that for the existence of heterogeneous equilibrium, pure solids or liquids must also be present, however small the amount may be, at equilibrium, but their concentrations or partial pressures do not appear in the expression of the equilibrium constant. In the reaction, Ag2O, S, plus 2HNO3, Ac, 2AgNO3, Ac, plus H2O, L, Kc is equal to AgNO3, 232HNO. Problem 7.6. The value of Kp for the reaction, Co2, G, plus C, S, 2 Co, G, is 3.0 at 1000 K. If initially PCO2 is equal to 0.48 bar and PCO is equal to 0 bar and pure graphite is present, calculate the equilibrium partial pressures of Co and Co2. Solution for the reaction, let X be the decrease in pressure of Co2, then Co2, G, plus C, S, 2 Co, G, initial pressure, 0.48 bar 0 units of equilibrium constant. The value of equilibrium constant Kc can be calculated by substituting the concentration terms in mol L, and for Kp partial pressure is substituted in Pa, Kpa, bar or atm. This results in units of equilibrium constant based on molarity or pressure, unless the exponents of both the numerator and denominator are same. For the reactions, H2, G, plus I2, G, 2 high, Kc and Kp have no unit. N2O4, G, 2 no 2, G, Kc has unit mol L and Kp has unit bar. Equilibrium constants can also be expressed as dimensionless quantities if the standard state of reactants and products are specified. For a pure gas, the standard state is 1 bar. Therefore, a pressure of 4 bar in standard state can be expressed as 4 bar 1 bar is equal to 4, which is a dimensionless number. Standard state C0 for a solute is 1 molar solution and all concentrations can be measured with respect to it. The numerical value of equilibrium constant depends on the standard state chosen. Thus, in this system both Kp and Kc are dimensionless quantities but have different numerical values due to different standard states. 2019-20 205 Equilibrium at equilibrium 0.48x bar 2x bar Kp is equal to Pp co 2 Kp is equal to 2x 2 0.48 kiss smiley is equal to 3 4x2 is equal to 3 0.48 kiss smiley 4x2 is equal to 1.44x 4x2 plus 3x 1.44 is equal to 0. A is equal to 4, B is equal to 3, C is equal to 1.44x B B A C A is equal to plus or minus 2 4 2 is equal to 3 plus or minus 3 2 4 4 1.44 2 times 4 is equal to 3 plus or minus 5.66, 8 is equal to 3 plus 5.66, 8. As value of x cannot be negative, hence we neglect that value. X is equal to 2.66, 8 is equal to 0.33. The equilibrium partial pressures are PCO2 is equal to 2x is equal to 2 times 0.33 is equal to 0.66 bar PCO2 is equal to 0.48 x is equal to 0.48 0.33 is equal to 0.15 bar 5. The equilibrium constant K for a reaction is related to the equilibrium constant of the corresponding reaction, whose equation is obtained by multiplying or dividing the equation for the original reaction by a small integer. Let us consider applications of equilibrium constant to times predict the extent of a reaction on the basis of its magnitude, times predict the direction of the reaction, and times calculate equilibrium concentrations. 7th June 2001 Predicting the extent of a reaction. The numerical value of the equilibrium constant for a reaction indicates the extent of the reaction. But it is important to note that an equilibrium constant does not give any information about the rate at which the equilibrium is reached. The magnitude of Kc or Kp is directly proportional to the concentrations of products, as these appear in the numerator of equilibrium constant expression, and inversely proportional to the concentrations of the reactants, these appear in the denominator. This implies that a high value of K is suggestive of a high concentration of products and vice versa. We can make the following generalizations concerning the composition of equilibrium mixtures. Times if Kc 103, products predominate over reactants, i.e., if Kc is very large, the reaction proceeds nearly to completion. Consider the following examples. The reaction of H2 with O2 at 500 K has a very large equilibrium constant. Kc is equal to 2.4 times 1047. B. H2, G, plus Cl2, G, 2HCl, G, at 300 K has Kc is equal to 4.0 times 1031. C. H2, G, plus Br2, G, 2HBr, G. At 300 K, Kc is equal to 5.4 times 1018 times if Kc, 10.3, reactants predominate over products, i.e., if Kc is very small, the reaction proceeds rarely. Consider the following examples. 7.6 Applications of equilibrium constants. Before considering the applications of equilibrium constants, let us summarize the important features of equilibrium constants as follows. One expression for equilibrium constant is applicable only when concentrations of the reactants and products have attained constant value at equilibrium state. 2. The value of equilibrium constant is independent of initial concentrations of the reactants and products. 3. Equilibrium constant is temperature dependent, having one unique value for a particular reaction represented by a balanced equation at a given temperature. 4. The equilibrium constant for the reverse reaction is equal to the inverse of the equilibrium constant for the forward reaction. 2019-20. 206 Chemistry. The decomposition of H2O into H2 and O2 at 500 K has a very small equilibrium constant. Kc is equal to 4.1 times 1048 B N2 G plus O2 G 2 no G. At 298 K has Kc is equal to 4.8 times 1031 times if Kc is in the range of 10.3 to 103. Appreciable concentrations of both reactants and products are present. Consider the following examples. A. For reaction of H2 with I2 to give high, Kc is equal to 57.0 at 700 K. B. Also, gas phase decomposition of N2O4 to number 2 is another reaction with a value of Kc is equal to 4.64 times 10.3 at 25 degrees Celsius, which is neither too small nor too large. Hence, equilibrium mixtures contain appreciable concentrations of both N2O4 and number 2. These generalizations are illustrated in Fig. 7.6. If Qc is equal to Kc, the reaction mixture is already at equilibrium. Consider the gaseous reaction of H2 with I2 H2, G, plus I2, G, 2 high, G. Kc is equal to 57.0 at 700 K. Suppose we have molar concentrations, H2, T is equal to 0.10 m, I2, T is equal to 0.20 m and high, T is equal to 0.40 m. The subscript T on the concentration symbols means that the concentrations were measured at some arbitrary time T, not necessarily at equilibrium. Thus, the reaction quotient, Qc at this stage of the reaction is given by Qc is equal to high, T2, H2, T, I2, T is equal to 0.40 to 0.10 times 0.20 is equal to 8.0. Now, in this case, Qc, 8.0, does not equal Kc, 57.0, so the mixture of H2, G, I2, G, and high, G, is not at equilibrium, that is, more H2, G, and I2, G, will react to form more high, G, and their concentrations will decrease till Qc is equal to Kc. The reaction quotient, Qc, is useful in predicting the direction of reaction by comparing the values of Qc and Kc. Thus, we can make the following generalizations concerning the direction of the reaction. Fig. 7.7. Fig.7.6 Dependence of extent of reaction on Kc 7th June 2002 Predicting the direction of the reaction. The equilibrium constant helps in predicting the direction in which a given reaction will proceed at any stage. For this purpose, we calculate the reaction quotient Q. The reaction quotient, Q, Qc with molar concentrations and Qp with partial pressures, is defined in the same way as the equilibrium constant Kc, except that the concentrations in Qc are not necessarily equilibrium values. For a general reaction, AA plus BBC C plus DD, 7.19, Qc is equal to C, D, A, B, 7.20, then, if Qc, Kc, the reaction will proceed in the direction of reactants, reverse reaction. If Qc, Kc, the reaction will proceed in the direction of the products, forward reaction. Fig. 7.7 Predicting the direction of the reaction times if Qc, Kc, net reaction goes from left to right times if Qc, Kc, net reaction goes from right to left. Times if Qc is equal to Kc, no net reaction occurs. Problem 7.7 The value of Kc for the reaction 2AB plus C is 2 times 10^3. At a given time, the composition of reaction mixture is A is equal to B is equal to C is equal to 3 times 10^4 m. In which direction the reaction will proceed? 2019-20. Equilibrium. The total pressure at equilibrium was found to be 9.15 bar. Calculate Kc, Kp and partial pressure at equilibrium. Solution. We know PV is equal to nRT total volume, V is equal to 1L molecular mass of N2O4 is equal to 92 G number of moles is equal to 13.8 G 92 G is equal to 0.15 of the gas, N, gas constant, R, is equal to 0.083 bar L mol 1 K 1 temperature, T, is equal to 400 kPV is equal to nRTP times 1L is equal to 0.15 mol times 0.083 bar L mol 1 K 1 times 400 kP is equal to 4.98 bar N2O4 to know to initial pressure, 4.98 bar 0 at equilibrium, 4.98 kiss smiley bar 2x bar hence, total at equilibrium is equal to Pn2O4 plus PnO2 9.15 is equal to 4.98 kiss smiley plus 2x 9.15 is equal to 4.98 plus xx is equal to 9.15 4.98 is equal to 4.17 bar partial pressures at equilibrium are Pn2O4 is equal to 4.98 4.17 is equal to 0.81 bar PnO2 is equal to 2x is equal to 2 times 4.17 is equal to 8.34 bar kPpp no NO is equal to 224 2 is equal to 8.34 to 0.81 is equal to 85.87 kP is equal to Kc, RT. N 85.87 is equal to Kc, 0.083 times 400, 1 Kc is equal to 2.586 is equal to 2.6 Problem 7.93.00 mole of PCl5 kept in 1L closed reaction vessel was allowed to attain equilibrium at 380 K. Calculate composition of the mixture at equilibrium. Kc is equal to 1.80 solution PCl5 PCl3 plus Cl2 initial concentration, 3.000 solution for the reaction. The reaction quotient Qc is given by Qc is equal to B, C, A, 2 as A is equal to B is equal to C is equal to 3 times 10 4 mqz is equal to 3 times 10 4, 3 times 10 4, 3 times 10 4, 2 is equal to 1 as qz, kc, so the reaction will proceed in the reverse direction. 7th June 2003 Calculating equilibrium concentrations in case of a problem in which we know the initial concentrations but do not know any of the equilibrium concentrations. The following 3 steps Calculating equilibrium concentrations in case of a problem in which we know the initial concentrations but do not know any of the equilibrium concentrations. The following 3 steps shall be followed. Step 1. Write the balanced equation for the reaction. Step 2. Under the balanced equation, make a table that lists for each substance involved in the reaction, A, the initial concentration, b. the change in concentration on going to equilibrium, and c. the equilibrium concentration. In constructing the table, define X as the concentration, mol L, of one of the substances that reacts on going to equilibrium, then use the stoichiometry of the reaction to determine the concentrations of the other substances in terms of X. Step 3. Substitute the equilibrium concentrations into the equilibrium equation for the reaction and solve for X. If you are to solve a quadratic equation, choose the mathematical solution that makes chemical sense. Step 4. Calculate the equilibrium concentrations from the calculated value of X. Step 5. Check your results by substituting them into the equilibrium equation. Problem 7.813.8 G of N2O4 was placed in a 1L reaction vessel at 400 K and allowed to attain equilibrium N2O4, G, 202, G, 2019-20. 208 Chemistry. Let X mol per liter of PCl5 be dissociated at equilibrium 3-X, XXKC is equal to PCl3, Cl2, PCl5, 1.8 is equal to X2, 3 kiss smiley X2 plus 1.8 X 5.4 is equal to 0 X is equal to 1.8 plus or minus 1.8, 2.4, 5.4, 2X is equal to 1.8 plus or minus 3.24 plus 21.6, 2X is equal to 1.8 plus or minus 4.98, 2X is equal to 1.8 plus 4.98, 2 is equal to 1.59, PCl5 is equal to 3.0, X is equal to 31.59 is equal to 1.41 m, PCl3 is equal to Cl2 is equal to X is equal to 1.59 m. 7.7 Relationship between equilibrium constant K, reaction quotient Q and Gibbs energy G. The value of Kc for a reaction does not depend on the rate of the reaction. However, as you have studied in Unit 6, it is directly related to the thermodynamics of the reaction and in particular, to the change in Gibbs energy, G. If times G is negative, then the reaction is spontaneous and proceeds in the forward direction. Times G is positive, then reaction is considered non-spontaneous. Instead, as reverse reaction would have a negative G, the products of the forward reaction shall be converted to the reactants. Times G is 0. Reaction has achieved equilibrium. At this point, there is no longer any free energy left to drive the reaction. A mathematical expression of this thermodynamic view of equilibrium can be described by the following equation: G is equal to G plus RT ln Q, 7.21, where G is standard Gibbs energy. At equilibrium, when G is equal to 0 and Q is equal to Kc, the equation 7.21 becomes G is equal to G plus RT ln K is equal to 0. G is equal to RT ln K, 7.22, ln K is equal to G RT. Taking antilog of both sides, we get K is equal to Eg RT, 7.23, hence, using the equation 7.23, the reaction spontaneity can be interpreted in terms of the value of G times if G 0, then GRT is positive, and 1, making K 1, which implies a spontaneous reaction or the reaction which proceeds in the forward direction to such an extent that the products are present predominantly. Times if G 0, then GRT is negative, and 1, that is, K 1, which implies a non-spontaneous reaction or a reaction which proceeds in the forward direction to such a small degree that only a very minute quantity of product is formed. Problem 7.10. The value of G for the phosphorylation of glucose in glycolysis is 13.8 kJ/mol. Find the value of Kc at 298 K. Solution: G is equal to 13.8 kJ/mol is equal to 13.8 times 103 J/mol. Also, G is equal to RT ln Kc. Hence, ln Kc is equal to 13.8 times 103 J/mol, 8.314 J/mol. 1 K 1 times 298 K. ln Kc is equal to 5.569 Kc is equal to E5.569 Kc is equal to 3.81 times 10^3. Problem 7.11. Hydrolysis of sucrose gives sucrose plus H2O glucose plus fructose. Equilibrium constant Kc for the reaction is 2 times 1013 at 300 K. Calculate G at 300 K. Solution: G is equal to RT ln Kc. G is equal to 8.314 J/mol. 1 K 1 times 300 K times ln 2 times 1013. G is equal to 7.64 times 104 J/mol. 7.8 Factors affecting equilibria. One of the principal goals of chemical synthesis is to maximize the conversion of the reactants. 2019 to 20. 209. Equilibrium Fig. 7.8 Effect of addition of H2 on change of concentration for the reactants and products in the reaction. H2, G, plus I2, G, to high, G, to products while minimizing the expenditure of energy. This implies maximum yield of products at mild temperature and pressure conditions. If it does not happen, then the experimental conditions need to be adjusted. For example, in the Haber process for the synthesis of ammonia from N2 and H2, the choice of experimental conditions is of real economic importance. Annual world production of ammonia is about 100 million tons, primarily for use as fertilizers. Equilibrium constant, Kc, is independent of initial concentrations. But if a system at equilibrium is subjected to a change in the concentration of one or more of the reacting substances, then the system is no longer at equilibrium, and net reaction takes place in some direction until the system returns to equilibrium once again. Similarly, a change in temperature or pressure of the system may also alter the equilibrium. In order to decide what course the reaction adopts and make a qualitative prediction about the effect of a change in conditions on equilibrium, we use Le Chatelier's principle. It states that a change in any of the factors that determine the equilibrium conditions of a system will cause the system to change in such a manner so as to reduce or to counteract the effect of the change. This is applicable to all physical and chemical equilibria. We shall now be discussing factors which can influence the equilibrium. 7th August 2001 Effect of concentration change in general. When equilibrium is disturbed by the addition-removal of any reactant products, Le Chatelier's principle predicts that times the concentration stress of an added reactant product is relieved by net reaction in the direction that consumes the added substance, times the concentration stress of a removed reactant product is relieved by net reaction in the direction that replenishes the removed substance. Or in other words, when the concentration of any of the reactants or products in a reaction at equilibrium is changed, the composition of the equilibrium mixture changes so as to minimize the effect of concentration changes. Let us take the reaction H2, G, plus I2, G, to high, G. If H2 is added to the reaction mixture at equilibrium, then the equilibrium of the reaction is disturbed. In order to restore it, the reaction proceeds in a direction wherein H2 is consumed, i.e., more of H2 and I2 react to form high, and finally the equilibrium shifts in right, forward, direction, Fig. 7.8. This is in accordance with the Le Chatelier's principle, which implies that in case of addition of a reactant product, a new equilibrium will be set up in which the concentration of the reactant product should be less than what it was after the addition but more than what it was in the original mixture. The same point can be explained in terms of the reaction quotient, QC. QC is equal to high 2 H2 I2 2019 to 20. (210) Chemistry addition of hydrogen at equilibrium results in value of QC being less than Kc. Thus, in order to attain equilibrium again reaction moves in the forward direction. Similarly, we can say that removal of a product also boosts the forward reaction and increases the concentration of the products, and this has great commercial application in cases of reactions where the product is a gas or a volatile substance. In case of manufacture of ammonia, ammonia is liquefied and removed from the reaction mixture so that reaction keeps moving in forward direction. Similarly, in the large-scale production of CaO, used as important building material, from CaCO3, constant removal of CO2 from the kiln drives the reaction to completion. It should be remembered that continuous removal of a product maintains QC at a value less than Kc and reaction continues to move in the forward direction. Effect of concentration and experiment. This can be demonstrated by the following reaction: Fe3 plus Ac plus SCN, Ac, Fe, SCN, 2 plus Ac, 7.24, yellow colorless deep red, 7.25, a reddish color appears on adding 2 drops of 0.002 m potassium thiosinate solution to 1 ml of 0.2 m iron, 3, nitrate solution due to the formation of Fe, SCN, 2+. The intensity of the red color becomes constant on attaining equilibrium. This equilibrium can be shifted in either forward or reverse directions depending on our choice of adding a reactant or a product. The equilibrium can be shifted in the opposite direction by adding reagents that remove Fe3+ or SCN ions. For example, oxalic acid, H2C2O4, reacts with Fe3+ ions to form the stable complex ion, Fe, C2O4, 3, thus decreasing the concentration of free Fe3+, Ac. In accordance with the Le Chatelier's principle, the concentration stress of removed Fe3+ is relieved by dissociation of Fe, SCN, 2+ to replenish the Fe3+ ions. Because the concentration of Fe, SCN, 2+ decreases, the intensity of red color decreases. Addition of Ac, HgCl2 also decreases red color because Hg2+ reacts with SCN ions to form stable complex ion, Hg, SCN, 4, 2. Removal of free SCN, Ac, shifts the equilibrium in equation 7.24 from right to left to replenish SCN ions. Addition of potassium thiocyanate on the other hand increases the color intensity of the solution as it shifts the equilibrium to right. 7th August 2002 Effect of pressure change. A pressure change obtained by changing the volume can affect the yield of products in case of a gaseous reaction where the total number of moles of gaseous reactants and total number of moles of gaseous products are different. In applying Le Chatelier's principle to a heterogeneous equilibrium, the effect of pressure changes on solids and liquids can be ignored because the volume and concentration of a solution liquid is nearly independent of pressure. Consider the reaction Co G plus 3H2 G CH4 G plus H2O G. Here, 4 mole of gaseous reactants Co plus 3H2 become 2 mole of gaseous products CH4 plus H2O. Suppose equilibrium mixture for above reaction kept in a cylinder fitted with a piston at constant temperature is compressed to 1/2 of its original volume. Then, total pressure will be doubled, according to PV is equal to constant. The partial pressure and therefore, concentration of reactants and products have changed and the mixture is no longer at equilibrium. The direction in which the reaction goes to re-establish equilibrium can be predicted by applying the Le Chatelier's principle. Since pressure has doubled, the equilibrium now shifts in the forward direction, a direction in which the number of moles of the gas or pressure decreases. We know pressure is proportional to moles of the gas. This can also be understood by using reaction quotient, QC. Let Co, H2, CH4, and H2O be the molar concentrations at equilibrium for methanation reaction. When 2019 to 20. 211 Equilibrium Fig. 7.9 Effect of temperature on equilibrium for the reaction, 2NO2, G, N2O4, G. Volume of the reaction mixture is halved, the partial pressure and the concentration are doubled. We obtain the reaction quotient by replacing each equilibrium concentration by double its value. QC is equal to CHGHOG Co GHG4223 as QC, Kc. The reaction proceeds in the forward direction. In reaction C, S, plus Co2, G, 2 Co, G. When pressure is increased, the reaction goes in the reverse direction because the number of moles of gas increases in the forward direction. 7th August 2003 Effect of inert gas addition. If the volume is kept constant and an inert gas such as argon is added which does not take part in the reaction, the equilibrium remains undisturbed. It is because the addition of an inert gas at constant volume does not change the partial pressures or the molar concentrations of the substance involved in the reaction. The reaction quotient changes only if the added gas is a reactant or product involved in the reaction. 7th August 2004 Effect of temperature change. Whenever an equilibrium is disturbed by a change in the concentration, pressure or volume, the composition of the equilibrium mixture changes because the reaction quotient, QC, no longer equals the equilibrium constant, Kc. However, when a change in temperature occurs, the value of equilibrium constant, Kc, is changed. In general, the temperature dependence of the equilibrium constant depends on the sign of H for the reaction, times the equilibrium constant for an exothermic reaction, negative H, decreases as the temperature increases, times the equilibrium constant for an endothermic reaction, positive H, increases as the temperature increases. Temperature changes affect the equilibrium constant and rates of reactions. Production of ammonia according to the reaction, N2, G, plus 3H2, G, 2NH3, G, H is equal to 92.38 kJ mol. 1 is an exothermic process. According to Le Chatelier's principle, raising the temperature shifts the equilibrium to left and decreases the equilibrium concentration of ammonia. In other words, low temperature is favorable for high yield of ammonia, but practically very low temperatures slow down the reaction and thus a catalyst is used. Effect of temperature and experiment. Effect of temperature on equilibrium can be demonstrated by taking number 2 gas, brown in color, which dimerizes into N2O4 gas, colorless. To know 2, G, N2O4, G, H is equal to 57.2 kJ-mol 1 number 2 gas prepared by addition of quaternings to conc. HNO3 is collected in 2 5 ml test tubes, ensuring same intensity of color of gas in each tube, and stopper sealed with araldite. 3 250 ml beakers 1, 2 and 3 containing freezing mixture, water at room temperature and hot water, 363 K, respectively, are taken. Fig 7.9. Both the test tubes are placed in beaker 2 for 8 to 10 minutes. After this, one is placed in beaker 1 and the other in beaker 3. The effect of temperature on direction of reaction is depicted very well in this experiment. At low temperatures in beaker 1, the forward reaction of formation of N2O4 is preferred, as reaction is exothermic, and thus, intensity of brown color due to number 2 decreases. While in beaker 3, high temperature favors the reverse reaction of 2019 to 20. (212) Chemistry formation of number 2 and thus, the brown color intensifies. Effect of temperature can also be seen in an endothermic reaction, Co, H2O, 6, 3 plus, Ac, plus 4Cl, Ac, CoCl4, 2, Ac, plus 6H2O, L, pink colorless blue at room temperature. The equilibrium mixture is blue due to CoCl4, 2. When cooled in a freezing mixture, the color of the mixture turns pink due to Co, H2O, 6, 3 plus. 7th August 2005 Effect of a catalyst. A catalyst increases the rate of the chemical reaction by making available a new low-energy pathway for the conversion of reactants to products. It increases the rate of forward and reverse reactions that pass through the same transition state and does not affect equilibrium. Catalyst lowers the activation energy for the forward and reverse reactions by exactly the same amount. Catalyst does not affect the equilibrium composition of a reaction mixture. It does not appear in the balanced chemical equation or in the equilibrium constant expression. Let us consider the formation of NH3 from dinitrogen and the hydrogen, which is highly exothermic reaction and proceeds with decrease in total number of moles formed as compared to the reactants. Equilibrium constant decreases with increase in temperature. At low temperature rate decreases and it takes long time to reach at equilibrium, whereas high temperatures give satisfactory rates but poor yields. German chemist Fritz Haber discovered that a catalyst consisting of iron catalyzed the reaction to occur at a satisfactory rate at temperatures where the equilibrium concentration of NH3 is reasonably favorable. Since the number of moles formed in the reaction is less than those of reactants, the yield of NH3 can be improved by increasing the pressure. Optimum conditions of temperature and pressure for the synthesis of NH3 using catalyst are around 500 degrees Celsius and 200 atm. Similarly, in manufacture of sulfuric acid by contact process, 2SO2, G, plus O2, G, 2SO3, G, Kc is equal to 1.7 times 1026, though the value of K is suggestive of reaction going to completion, but practically the oxidation of SO2 to SO3 is very slow. Thus, platinum or divnadium pentaoxide, V2O5, is used as catalyst to increase the rate of the reaction. Note: If a reaction has an exceedingly small k, a catalyst would be of little help. 7.9 Ionic equilibrium in solution under the effect of change of concentration on the direction of equilibrium. You have incidentally come across with the following equilibrium, which involves ions Fe3+, Ac plus SCN, Ac, Fe, SCN, 2+, Ac. There are numerous equilibria that involve ions only. In the following sections we will study the equilibria involving ions. It is well known that the aqueous solution of sugar does not conduct electricity. However, when common salt, sodium chloride, is added to water, it conducts electricity. Also, the conductance of electricity increases with an increase in concentration of common salt. Michael Faraday classified the substances into two categories based on their ability to conduct electricity. One category of substances conduct electricity in their aqueous solutions and are called electrolytes, while the other do not and are thus referred to as non-electrolytes. Faraday further classified electrolytes into strong and weak electrolytes. Strong electrolytes on dissolution in water are ionized almost completely, while the weak electrolytes are only partially dissociated. For example, an aqueous solution of sodium chloride is comprised entirely of sodium ions and chloride ions, while that of acetic acid mainly contains unionized acetic acid molecules and only some acetate ions and hydronium ions. This is because there is almost 100% ionization in case of sodium chloride as compared to less than 5% ionization of acetic acid, which is a weak electrolyte. It should be noted that in weak electrolytes, equilibrium is 2019 to 20. 213 Equilibrium Fig.7.10 Dissolution of sodium chloride in water. Na plus and Cl ions are established by their hydration with polar water molecules. Established between ions and the unionized molecules. This type of equilibrium involving ions in aqueous solution is called Ionic Equilibrium. Acids, bases and salts come under the category of electrolytes and may act as either strong or weak electrolytes. 7.10 Acids, bases and salts. Acids, bases and salts find widespread occurrence in nature. Hydrochloric acid present in the gastric juice is secreted by the lining of our stomach in a significant amount of 1.2-1.5 LD and is essential for digestive processes. Acetic acid is known to be the main constituent of vinegar. Lemon and orange juices contain citric and ascorbic acids, and tartaric acid is found in tamarind paste. As most of the acids taste sour, the word acid has been derived from a Latin word, acidus, meaning sour. Acids are known to turn blue litmus paper into red and liberate the hydrogen on reacting with some metals. Similarly, bases are known to turn red litmus paper blue, taste bitter and feel soapy. A common example of a base is washing soda used for washing purposes. When acids and bases are mixed in the right proportion, they react with each other to give salts. Some commonly known examples of salts are sodium chloride, barium sulfate, sodium nitrate. Sodium chloride, common salt, is an important component of our diet and is formed by reaction between hydrochloric acid and sodium hydroxide. It exists in solid state as a cluster of positively charged sodium ions and negatively charged chloride ions, which are held together due to electrostatic interactions between oppositely charged species. Fig.7.10. The electrostatic forces between two charges are inversely proportional to dielectric constant of the medium. Water, a universal solvent, possesses a very high dielectric constant of 80. Thus, when sodium chloride is dissolved in water, the electrostatic interactions are reduced by a factor of 80, and this facilitates the ions to move freely in the solution. Also, they are well separated due to hydration with water molecules. Faraday was born near London into a family of very limited means. At the age of 14 he was an apprentice to a kind bookbinder who allowed Faraday to read the books he was binding. Through a fortunate chance he became laboratory assistant to Dewey, and during 1813-4, Faraday accompanied him to the continent. During this trip he gained much from the experience of coming into contact with many of the leading scientists of the time. In 1825, he succeeded Dewey as director of the Royal Institution Laboratories, and in 1833 he also became the first Fullerian professor of chemistry. Faraday's first important work was on analytical chemistry. After 1821 much of his work was on electricity and magnetism and different electromagnetic phenomena. His ideas have led to the establishment of modern field theory. He discovered his two laws of electrolysis in 1834. Faraday was a very modest and kind-hearted person. He declined all honors and avoided scientific controversies. He preferred to work alone and never had any assistant. He disseminated science in a variety of ways, including his Friday evening discourses, which he founded at the Royal Institution. He has been very famous for his Christmas lecture on the chemical history of a candle. He published nearly 450 scientific papers. Michael Faraday, 17911867, comparing the ionization of hydrochloric acid with that of acetic acid in water, we find that though both of them are polar covalent 2019-20. 214 chemistry molecules. Former is completely ionized into its constituent ions, while the latter is only partially ionized, 5%. The extent to which ionization occurs depends upon the strength of the bond and the extent of solvation of ions produced. The terms dissociation and ionization have earlier been used with different meaning. Dissociation refers to the process of separation of ions in water already existing as such in the solid state of the solute, as in sodium chloride. On the other hand, ionization corresponds to a process in which a neutral molecule splits into charged ions in the solution. Here, we shall not distinguish between the two and use the two terms interchangeably. 7th October 2001 Arrhenius concept of acids and bases. According to Arrhenius theory, acids are substances that dissociates in water to give hydrogen ions H+, Ac, and bases are substances that produce hydroxyl ions O, Ac. The ionization of an acid HX, Ac, can be represented by the following equations: HX, Ac, H+, Ac, plus X, Ac, or HX, Ac, plus H2O, L, H3O plus, Ac, plus X, Ac. A bare proton, H+, is very reactive and cannot exist freely in aqueous solutions. Thus, it bonds to the oxygen atom of a solvent water molecule to give trigonal pyramidal hydronium ion, H3O plus, H, H2O plus, C box. In this chapter we shall use H+, Ac, and H3O+, Ac, interchangeably to mean the same I, a hydrated proton. Similarly, a base molecule like Mo ionizes in aqueous solution according to the equation Mo, Ac, M+, Ac, plus O, Ac, The hydroxyl ion also exists in the hydrated form in the aqueous solution. Arrhenius' concept of acid and base, however, suffers from the limitation of being applicable only to aqueous solutions and also does not account for the basicity of substances like ammonia which do not possess a hydroxyl group. 7th October 2002 The Bronsted-Lowry acids and bases. The Danish chemist, Johannes Bronsted, and the English chemist, Thomas M. Lowry gave a more general definition of acids and bases. According to Bronsted-Lowry theory, acid is a substance that is capable of donating a hydrogen ion H+, and bases are substances capable of accepting a hydrogen ion H+. In short, acids are proton donors and bases are proton acceptors. Consider the example of dissolution of NH3 in H2O represented by the following equation: hydronium and hydroxyl ions. Hydrogen ion by itself is a bare proton with very small size, 1015 m radius, and intense electric field, binds itself with the water molecule at one of the two available lone pairs on it, giving H3O+. This species has been detected in many compounds, e.g., H3O plus Cl, in the solid state. In aqueous solution, the hydronium ion is further hydrated to give species like H5O2+, H7O3+, and H9O4+. Similarly, the hydroxyl ion is hydrated to give several ionic species like H3O2, H5O3, and H7O4, etc. The basic solution is formed due to the presence of hydroxyl ions. In this reaction, water molecule acts as proton donor and ammonia molecule acts as proton acceptor and are thus called Lowry-Bronsted acid and H9O4 plus 2019-20. 215 Equilibrium. Svante Arrhenius, 1859-1927. Arrhenius was born near Uppsala, Sweden. He presented his thesis on the conductivities of electrolyte solutions to the University of Uppsala in 1884. For the next 5 years he traveled extensively and visited a number of research centers in Europe. In 1895 he was appointed professor of physics at the newly formed University of Stockholm, serving its rector from 1897 to 1902. From 1905 until his death he was director of physical chemistry at the Nobel Institute in Stockholm. He continued to work for many years on electrolytic solutions. In 1899 he discussed the temperature dependence of reaction rates on the basis of an equation, now usually known as Arrhenius equation. He worked in a variety of fields, and made important contributions to immunochemistry, cosmology, the origin of life, and the causes of Ice Age. He was the first to discuss the greenhouse effect, calling by that name. He received Nobel Prize in Chemistry in 1903 for his theory of electrolytic dissociation and its use in the development of chemistry. Base, respectively. In the reverse reaction, H+ is transferred from NH4+ to O. In this case, NH4+ acts as a Bronsted acid while O acted as a Bronsted base. The acid-base pair that differs only by one proton is called a conjugate acid-base pair. Therefore, O is called the conjugate base of an acid H2O and NH4+ is called conjugate acid of the base NH3. If Bronsted acid is a strong acid, then its conjugate base is a weak base and vice versa. It may be noted that conjugate acid has one extra proton and each conjugate base has one less proton. Consider the example of ionization of hydrochloric acid in water. HCl, Ac, acts as an acid by donating a proton to H2O molecule which acts as a base. Ammonia, it acts as an acid by donating a proton. Problem 7.12. What will be the conjugate basis for the following Bronsted acids, HF, H2SO4 and HCO3? Solution: the conjugate bases should have one proton less in each case, and therefore the corresponding conjugate bases are F, HSO4 and Co32 respectively. Problem 7.13. Write the conjugate acids for the following Bronsted bases, NH2, NH3 and HCO. Solution: the conjugate acid should have one extra proton in each case, and therefore the corresponding conjugate acids are NH3, NH4+ and HCO respectively. Problem 7.14. The species H2O, HCO3, HSO4 and NH3 can act both as Bronsted acids and bases. For each case give the corresponding conjugate acid and conjugate base. Solution: the answer is given in the following table. Species conjugate acid base H2O3O plus OHCO3 H2 CO3 CO32 HSO4 H2 SO4 SO42 NH3 NH4 plus NH2. It can be seen in the above equation that water acts as a base because it accepts the proton. The species H3O+ is produced when water accepts a proton from HCl. Therefore, Cl is a conjugate base of HCl and HCl is the conjugate acid of base Cl. Similarly, H2O is a conjugate base of an acid H3O+ and H3O+ is a conjugate acid of base H2O. It is interesting to observe the dual role of water as an acid and a base. In case of reaction with HCl, water acts as a base, while in case of 2019-20 216 Chemistry 7th October 2003 Lewis acids and bases. G. N. Lewis in 1923 defined an acid as a species which accepts electron pair and base which donates an electron pair. As far as bases are concerned, there is not much difference between Bronsted-Lowry and Lewis concepts, as the base provides a lone pair in both the cases. However, in Lewis concept many acids do not have proton. A typical example is reaction of electron-deficient species BF3 with NH3. BF3 does not have a proton but still acts as an acid and reacts with NH3 by accepting its lone pair of electrons. The reaction can be represented by BF3 plus NH3 BF3. NH3 electron-deficient species like AlCl3, CO3+, Mg2+, etc. can act as Lewis acids, while species like H2O, NH3, O etc. which can donate a pair of electrons, can act as Lewis bases. Problem 7.15. Classify the following species into Lewis acids and Lewis bases and show how these act as such. A, Ho, B, F, C, H plus, D, BCl3 solution. A, hydroxyl ion is a Lewis base as it can donate an electron lone pair. O, B, fluoride ion acts as a Lewis base as it can donate any one of its 4 electron lone pairs. C, a proton is a Lewis acid as it can accept a lone pair of electrons from bases like hydroxyl ion and fluoride ion. D, BCl3 acts as a Lewis acid as it can accept a lone pair of electrons from species like ammonia or amine molecules. 7.11 Ionization of acids and bases. Arrhenius concept of acids and bases becomes useful in case of ionization of acids and bases, as mostly ionizations in chemical and biological systems occur in aqueous medium. Strong acids like perchloric acid, HCl4, hydrochloric acid, HCl, hydrobromic acid, HBr, hydroiodic acid, high, nitric acid, HNO3, and sulfuric acid, H2SO4, are termed strong because they are almost completely dissociated into their constituent ions in an aqueous medium, thereby acting as proton, H+, donors. Similarly, strong bases like lithium hydroxide, LiOH, sodium hydroxide, NaOH, potassium hydroxide, KOH, cesium hydroxide, CSOH, and barium hydroxide BaO2 are almost completely dissociated into ions in an aqueous medium giving hydroxyl ions, O. According to Arrhenius concept, they are strong acids and bases as they are able to completely dissociate and produce H3O+ and O ions respectively in the medium. Alternatively, the strength of an acid or base may also be gauged in terms of Bronsted-Lowry concept of acids and bases, wherein a strong acid means a good proton donor and a strong base implies a good proton acceptor. Consider the acid-base dissociation equilibrium of a weak acid H plus H2O, L, H3O+, AC, plus A, AC. Conjugate acid-base in section 7th October 2002 we saw that acid, or base, dissociation equilibrium is dynamic involving a transfer of proton in forward and reverse directions. Now, the question arises that if the equilibrium is dynamic, then with passage of time which direction is favored? What is the driving force behind it? In order to answer these questions, we shall deal into the issue of comparing the strengths of the two acids, or bases, involved in the dissociation equilibrium. Consider the two acids H and H3O+ present in the above-mentioned acid dissociation equilibrium. We have to see which amongst them is a stronger proton donor. Whichever exceeds in its tendency of donating a proton over the other shall be termed as the stronger acid, and the equilibrium will shift in the direction of weaker acid. Say, if H is a stronger acid than H3O+, then H will donate protons and not H3O+, and the solution will mainly contain A and H3O+ ions. The equilibrium moves in the direction of formation of weaker acid and weaker base 2019-20. 217 equilibrium because the stronger acid donates a proton to the stronger base. It follows that as a strong acid dissociates completely in water, the resulting base formed would be very weak, i.e., strong acids have very weak conjugate bases. Strong acids like perchloric acid, HCl4, hydrochloric acid, HCl, hydrobromic acid, HBr, hydroiodic acid, high, nitric acid, HNO3, and sulfuric acid, H2SO4, will give conjugate base ions close O4, Cl, Br, I, number 3 and HSO4, which are much weaker bases than H2O. Similarly, a very strong base would give a very weak conjugate acid. On the other hand, a weak acid say H is only partially dissociated in aqueous medium and thus, the solution mainly contains undissociated H molecules. Typical weak acids are nitrous acid, HNO2, hydrofluoric acid, HF, and acetic acid, CH3Q. It should be noted that the weak acids have very strong conjugate bases. For example, NH2, O2 and H are very good proton acceptors and thus, much stronger bases than H2O. Certain water-soluble organic compounds like phenolphthalein and bromothymol blue behave as weak acids and exhibit different colors in their acid, HN, and conjugate base, in, forms. HN, AC, plus H2O, L, H3O plus, AC, plus in, AC. Acid conjugate indicator acid base color A color B. Such compounds are useful as indicators in acid base titrations and finding out H+ ion concentration. 7th November 2001. The ionization constant of water and its ionic product. Some substances like water are unique in their ability of acting both as an acid and a base. We have seen this in case of water in section 7th October 2002. In presence of an acid, it accepts a proton and acts as the base, while in the presence of a base, B, it acts as an acid by donating a proton. In pure water, one H2O molecule donates proton and acts as an acid, and another water molecule accepts a proton and acts as a base at the same time. The following equilibrium exists: H2O, L, plus H2O, L, H3O plus, AC, plus O, AC. Acid-base conjugate acid-base. The dissociation constant is represented by K is equal to H3O plus O, H2O, 7.26. The concentration of water is omitted from the denominator as water is a pure liquid and its concentration remains constant. H2O is incorporated within the equilibrium constant to give a new constant, Kw, which is called the ionic product of water. Kw is equal to H plus O, 7.27. The concentration of H plus has been found out experimentally as 1.0 times 10^7 m at 298 K. And, as dissociation of water produces equal number of H plus and O ions, the concentration of hydroxyl ions, O, is equal to H plus, is equal to 1.0 times 10^7 m. Thus, the value of Kw at 298 K. Kw is equal to H3O plus O, is equal to 1 times 10^7, 2 is equal to 1 times 10^14 m2, 7.28. The value of Kw is temperature dependent as it is an equilibrium constant. The density of pure water is 1000 gl and its molar mass is 18.0 g mol. From this, the molarity of pure water can be given as H2O is equal to 1000 gl, 1 mol 18.0 g, is equal to 55.55 m. Therefore, the ratio of dissociated water to that of undissociated water can be given as 10^7, 55.55, is equal to 1.8 times 10^9 or tilde 2 in 10^9. Thus, equilibrium lies mainly towards undissociated water. We can distinguish acidic, neutral and basic aqueous solutions by the relative values of the H3O plus and O concentrations. Acidic, H3O plus, O, neutral, H3O plus, is equal to O, basic, H3O plus, O. 7th November 2002. The pH scale hydronium ion concentration in molarity is more conveniently expressed on a logarithmic scale known as the pH scale. The pH of a solution is defined as the negative logarithm to base 10 of the activity R plus of hydrogen 2019 to 20. (218) Chemistry ion. In dilute solutions, 0.01 m, activity of hydrogen ion, H+, is equal in magnitude to molarity represented by H+. It should be noted that activity has no units and is defined as is equal to H+, mol L1 from the definition of pH. The following can be written: pH is equal to log R plus is equal to log H plus mol L1. Thus, an acidic solution of HCl, 10 m, will have a pH is equal to 2. Similarly, a basic solution of NaOH having O is equal to 10 m and H3O plus is equal to 10 m will have a pH is equal to 10. At 25 degrees Celsius, pure water has a concentration of hydrogen ions, H plus, is equal to 10.7 m. Hence, the pH of pure water is given as pH is equal to log 10.7 is equal to 7. Acidic solutions possess a concentration of hydrogen ions, H plus, 10.7 m, while basic solutions possess a concentration of hydrogen ions, H plus, 10.7 m. Thus, we can summarize that acidic solution has pH 7, basic solution has pH 7, neutral solution has pH is equal to 7. Now again, consider the equation 7.28 at 298 kW is equal to H3O plus O is equal to 1014. Taking negative logarithm on both sides of equation, we obtain log Kw is equal to log H3O plus O is equal to log H3O plus log O is equal to log 1014. pKw is equal to pH plus pOH is equal to 14. 7.29. Note that although Kw may change with temperature, the variations in pH with temperature are so small that we often ignore it. pKw is a very important quantity for aqueous solutions and controls the relative concentrations of hydrogen and hydroxyl ions as their product is a constant. It should be noted that as the pH scale is logarithmic, a change in pH by just 1 unit also means change in H plus by a factor of 10. Similarly, when the hydrogen ion concentration H plus changes by a factor of 100, the value of pH changes by 2 units. Now you can realize why the change in pH with temperature is often ignored. Measurement of pH of a solution is very essential as its value should be known when dealing with biological and cosmetic applications. The pH of a solution can be found roughly with the help of pH paper that has different color in solutions of different pH. Nowadays pH paper is available with 4 strips on it. The different strips have different colors. Fig 7.11. At the same pH, the pH in the range of 1 to 14 can be determined with an accuracy of ~0.5 using pH paper. Fig. 7.11 pH paper with 4 strips that may have different colors at the same pH. For greater accuracy, pH meters are used. pH meter is a device that measures the pH-dependent electrical potential of the test solution within 0.001 precision. pH meters of the size of a writing pen are now available in the market. The pH of some very common substances are given in Table 7.5, page 212. Problem 7.16. The concentration of hydrogen ion in a sample of soft drink is 3.8 times 10^3 m. What is its pH? Solution pH is equal to log 3.8 times 10^3 is equal to log 3.8 plus log 10^3 is equal to 0.58 plus 3.0 is equal to 2.42 is equal to 2.42. Therefore, the pH of the soft drink is 2.42 and it can be inferred that it is acidic. Problem 7.17. Calculate pH of a 1.0 times 10^8 m solution of HCl 2019-20. Equilibrium Table 7.6. The ionization constants of some selected weak acids at 298 K. Acid ionization constant Ka hydrofluoric acid HF 3.5 times 10^4 nitrous acid HNO2 4.5 times 10^4 formic acid HQ 1.8 times 10^4 niacin C5H4 Ngu 1.5 times 10⁵ acetic acid, CH3Cu, 1.74 times 10⁵ benzoic acid, C6H5Cu, 6.5 times 10⁵ hypochlorous acid, HCl, 3.0 times 10⁸ hydrocyanic acid, HCN, 4.9 times 10⁻10 phenol, C6H5O, 1.3 times 10⁻10 solution to H2O, L, H3O+, AC, plus O, AC, Kw is equal to, O, H3O+, is equal to 1014 let, X is equal to, O, is equal to, H3O+, from H2O. The H3O+ concentration is generated, I, from the ionization of HCl dissolved i.e., HCl, AC, plus H2O, L, H3O+, AC, plus Cl, AC, and 2, from ionization of H2O. In these very dilute solutions, both sources of H3O+ must be considered. H3O+ is equal to 10⁸ plus X, Kw is equal to 10⁸ plus X, Kiss Smiley is equal to 1014 or X2 plus 10⁸ X 1014 is equal to 0, O is equal to X is equal to 9.5 times 10⁸, so pOH is equal to 7.02 and pH is equal to 6.98. 7th November 2003 Ionization constants of weak acids. Consider a weak acid HX that is partially ionized in the aqueous solution. The equilibrium can be expressed by HX, AC, plus H2O, L, H3O plus, AC, plus X, AC. Initial concentration, M, C00. Let alpha be the extent of ionization change, M, C alpha plus C alpha plus C alpha. Equilibrium concentration, M, C alpha C alpha C alpha. Here, C is equal to initial concentration of the undissociated acid, HX at time, T is equal to 0. Alpha is equal to extent up to which HX is ionized into ions. Using these notations, we can derive the equilibrium constant for the above discussed acid dissociation equilibrium. K is equal to C2 alpha to C, 1 alpha, is equal to C alpha to 1 alpha. K is called the dissociation or ionization constant of acid HX. It can be represented alternatively in terms of molar concentration as follows: K is equal to H plus X, HX, 7.30. At a given temperature T, K is a measure of the strength of the acid HX, i.e., larger the value of K, the stronger is the acid. K is a dimensionless quantity with the understanding that the standard state concentration of all species is 1 m. The values of the ionization constants of some selected weak acids are given in Table 7.6. Table 7.5 The pH of some common substances. Name of the fluid pH. Name of the fluid pH. Saturated solution of NaOH tilde 15 black coffee 5.00.1 m NaOH solution 13 tomato juice tilde 4.2 lime water 10.5 soft drinks and vinegar tilde 3.0 milk of magnesia 10 lemon juice tilde 2.2 egg white sea water 7.8 gastric juice tilde 1.2 human blood 7.41 mHCl solution tilde 0 milk 6.8 concentrated HCl tilde 1.0 human saliva 6.4. The pH scale for the hydrogen ion concentration has been so useful that besides pKw, it has been extended to other species and 2019 to 20. 220 chemistry quantities. Thus, we have pK is equal to log K 7.31, knowing the ionization constant K of an acid and its initial concentration C it is possible to calculate the equilibrium concentration of all species and also the degree of ionization of the acid and the pH of the solution. A general stepwise approach can be adopted to evaluate the pH of the weak electrolyte as follows. Step 1. The species present before dissociation are identified as Bronsted-Lowry acids bases. Step 2. Balanced equations for all possible reactions i.e., with a species acting both as acid as well as base are written. Step 3. The reaction with the higher Ka is identified as the primary reaction whilst the other is a subsidiary reaction. Step 4. Enlist in a tabular form the following values for each of the species in the primary reaction. A. Initial concentration. C. B. Change in concentration on proceeding to equilibrium in terms of alpha, degree of ionization. C. Equilibrium concentration. Step 5. Substitute equilibrium concentrations into equilibrium constant equation for principal reaction and solve for alpha. Step 6. Calculate the concentration of species in principal reaction. Step 7. Calculate pH is equal to log H3O plus. The above mentioned methodology has been elucidated in the following examples. Problem 7.18. The ionization constant of HF is 3.2 times 10⁴. Calculate the degree of dissociation of HF in its 0.02 m solution. Calculate the concentration of all species present, H3O plus, F and HF, in the solution and its pH. Solution. The following proton transfer reactions are possible. 1. HF plus H2O H3O plus FK is equal to 3.2 times 10⁴. H2O plus H2O H3O plus OKW is equal to 1.0 times 10⁴ as K, KW, 1, is the principal reaction. HF plus H2O H3O plus F initial concentration, M, 0.0200 change, M, 0.02 alpha plus 0.02 alpha plus 0.02 alpha equilibrium concentration, M, 0.02 0.02 alpha 0.02 alpha 0.02 alpha. Substituting equilibrium concentrations in the equilibrium reaction for principal reaction gives K is equal to 0.02 alpha, 2, 0.020.02 alpha, is equal to 0.02 alpha 2, 1 alpha, is equal to 3.2 times 10⁴. We obtain the following quadratic equation. Alpha 2 plus 1.6 times 10⁴ alpha 1.6 times 10⁴ is equal to 0. The quadratic equation in alpha can be solved and the two values of the roots are alpha is equal to plus 0.12 and 0.12. The negative root is not acceptable and hence alpha is equal to 0.12. This means that the degree of ionization, alpha is equal to 0.12. Then equilibrium concentrations of other species with HF, F and H3O plus are given by H3O plus is equal to F is equal to C. Alpha is equal to 0.02 times 0.12 is equal to 2.4 times 10⁵ m. HF is equal to C. 1 alpha is equal to 0.02, 1 0.12 is equal to 17.6 times 10⁵ m. pH is equal to log H plus is equal to log 2.4 times 10⁵ is equal to 2.62. Problem 7.19. The pH of 0.1 m monobasic acid is 4.50. Calculate the concentration of species H plus 2019-20. 221 Equilibrium Table 7.7 The values of the ionization constant of some weak bases at 298 K base kilobyte dimethylamine, CH3, 2NH5.4 times 10(4) trithylamine, C2H5, 3N6.45 times 10(5) ammonia, NH3 or NH4 or 1.77 times 10(5) quinine, a plant product, 1.10 times 10(6) pyridine, C5H5N 1.77 times 10(9) aniline, C6H5NH2 4.27 times 10(10) urea, Co, NH2, 1.3 times 10(14) A and Ha at equilibrium. Also, determine the value of Ka and pK of the monobasic acid. Solution pH is equal to log H plus, therefore, H plus is equal to 10, pH is equal to 10(4.50) is equal to 3.16 times 10(5), H plus is equal to A is equal to 3.16 times 10(5), thus, Ka is equal to H plus A, Ha, Equilibrium is equal to 0.1, 3.16 times 10 to 5, 0.1 Ka is equal to 3.16 times 10 5, 0.1 is equal to 1.0 times 10 8 pK is equal to log 10 8 is equal to 8. Alternatively, percent dissociation is another useful method for measure of strength of a weak acid and is given as percent dissociation is equal to Ha dissociated, Ha, initial times 100%, 7.32. Problem 7.20 Calculate the pH of 0.08 m. Solution of hypochlorous acid, HOCl. The ionization constant of the acid is 2.5 times 10(5). Determine the percent dissociation of HOCl. Solution HOCl, AC, plus H2O, L, H3O plus, AC, plus ClO, AC. Initial concentration, M, 0.0800 changed to reach equilibrium concentration, M, X plus X plus X equilibrium concentration, M, 0.08xxx Ka is equal to, H3O plus, ClO, HOCl, is equal to X2, 0.08x, as X, 0.08, therefore 0.08x 0.08x2 slash 0.08 is equal to 2.5 times 10(5) x2 is equal to 2.0 times 10(6), thus, x is equal to 1.41 times 10(3), H plus, is equal to 1.41 times 10(3) m. Therefore, percent dissociation is equal to, HOCl, dissociated, HOCl, initial, times 100 is equal to 1.41 times 10(3) times 1020.08 is equal to 1.76%. pH is equal to log, 1.41 times 10(3), is equal to 2.85. 7th November 2004 Ionization of weak bases. The ionization of base MO can be represented by equation, MO, AC, M plus, AC, plus O, AC. In a weak base there is partial ionization of MO into M plus and O. The case is similar to that of acid dissociation equilibrium. The equilibrium constant for base ionization is called base ionization constant and is represented by kilobyte. It can be expressed in terms of concentration in molarity of various species in equilibrium by the following equation: kilobyte is equal to M plus O mol 7.33. Alternatively, if C is equal to initial concentration of base and alpha is equal to degree of ionization of base, i.e. the extent to which the base ionizes. When equilibrium is reached, the equilibrium constant can be written as kilobyte is equal to C alpha 2C 1 alpha, is equal to C alpha 2, 1 alpha. The values of the ionization constants of some selected weak bases, kilobyte, are given in table 7.7. Many organic compounds like amines are weak bases. Amines are derivatives of ammonia in which one or more hydrogen atoms are replaced by another group. For example, methylamine, codeine, quinine, and 2019-20. 222 chemistry. Nicotine all behave as very weak bases due to their very small kilobyte. Ammonia produces O in aqueous solution, NH3, Ac, plus H2O, L, NH4 plus, Ac, plus O, Ac. The pH scale for the hydrogen ion concentration has been extended to get p kilobyte is equal to log kilobyte 7.34. Problem 7.21. The pH of 0.004 m hydrazine solution is 9.7. Calculate its ionization constant kilobyte and p kilobyte. Solution NH2 plus H2O NH2 NH3 plus O. From the pH we can calculate the hydrogen ion concentration. Knowing hydrogen ion concentration and the ionic product of water, we can calculate the concentration of hydroxyl ions. Thus we have H plus is equal to antilog pH is equal to antilog 9.7 is equal to 1.67 times 1010 O is equal to kW. H plus is equal to 1 times 1014. 1.67 times 1010 is equal to 5.98 times 105. The concentration of the corresponding hydrazinium ion is also the same as that of hydroxyl ion. The concentration of both these ions is very small, so the concentration of the undissociated base can be taken equal to 0.004 m. Thus, kilobyte is equal to NH2 NH3 plus O NH2 NH2 is equal to 5.98 times 105 to 0.004 is equal to 8.96 times 107. P kilobyte is equal to log kilobyte is equal to log 8.96 times 107 is equal to 6.04. Problem 7.22. Calculate the pH of the solution in which 0.2 m NH4Cl and 0.1 m NH3 are present. The p kilobyte of ammonia solution is 4.75. Solution NH3 plus H2O NH4 plus O. The ionization constant of NH3 kilobyte is equal to antilog p kilobyte. I kilobyte is equal to 104.75 is equal to 1.77 times 105 m NH3 plus H2O NH4 plus O. Initial concentration m 0.10 0.200 changed to reach equilibrium m x plus x at equilibrium m 0.10 x 0.20 plus x kilobyte is equal to NH4 plus O NH3 is equal to 0.20 plus x kiss smiley 0.1 kiss smiley is equal to 1.77 times 105. As kilobyte is small, we can neglect x in comparison to 0.1 m and 0.2 m. Thus, O is equal to x is equal to 0.88 times 105. Therefore, H plus is equal to 1.12 times 109. pH is equal to log H plus is equal to 8.95. 7th November 2005. Relation between Ka and kilobyte. As seen earlier in this chapter, Ka and kilobyte represent the strength of an acid and a base, respectively. In case of a conjugate acid-base pair, they are related in a simple manner so that if one is known, the other can be deduced. Considering the example of NH4 plus and NH3, we see NH4 plus Ac plus H2O, L, H3O plus, Ac, plus NH3, Ac, Ca is equal to, H3O plus, NH3, NH4 plus, is equal to 5.6 times 10 NH3, Ac, plus H2O, L, NH4 plus, Ac, plus O, Ac, kilobyte sad smiley NH4 plus, O, NH3 is equal to 1.8 times 10⁵ net, 2 H2O, L, H3O plus, Ac, plus O, Ac, Kw is equal to, H3O plus, O, is equal to 1.0 times 10⁻14 m, where Ca represents the strength of NH4 plus as an acid and kilobyte represents the strength of NH3 as a base. It can be seen from the net reaction that the equilibrium constant is equal to the product of equilibrium constants Ca and kilobyte for the reactions added. Thus, Ca times kilobyte is equal to H3O plus, NH3, NH4 plus, times, NH4 plus, O, NH3, is equal to, H3O plus, O, is equal to Kw is equal to, 5.6 x 10 times, 1.8 times 10⁵, is equal to 1.0 times 10⁻14 m 2019 to 20. Double 2-3 equilibrium. This can be extended to make a generalization. The equilibrium constant for a net reaction obtained after adding two or more reactions equals the product of the equilibrium constants for individual reactions. Knet is equal to K1 times K2 times 3.35. Similarly, in case of a conjugate acid-base pair, Ca times kilobyte is equal to Kw, 7.36, knowing one, the other can be obtained. It should be noted that a strong acid will have a weak conjugate base and vice versa. Alternatively, the above expression Kw is equal to Ca times kilobyte can also be obtained by considering the base dissociation equilibrium reaction, B, Ac, plus H2O, L, BH plus, Ac, plus O, Ac, kilobyte is equal to, BH plus, O, B. As the concentration of water remains constant, it has been omitted from the denominator and incorporated within the dissociation constant. Then multiplying and dividing the above expression by H plus, we get kilobyte is equal to BH plus O, H plus, B, H plus, is equal to O, H plus, BH plus, B, H plus, is equal to Kw. Ca or Ca times kilobyte is equal to Kw. It may be noted that if we take negative logarithm of both sides of the equation, then pK values of the conjugate acid and base are related to each other by the equation. pK plus p kilobyte is equal to pKw is equal to 14 at 298 K. Problem 7.23. Determine the degree of ionization and pH of a 0.05 m of ammonia solution. The ionization constant of ammonia can be taken from table 7.7. Also, calculate the ionization constant of the conjugate acid of ammonia. Solution. The ionization of NH3 in water is represented by equation NH3 plus H2O NH4 plus O. We use equation 7.33 to calculate hydroxyl ion concentration. O is equal to C alpha is equal to 0.05 alpha kilobyte is equal to 0.05 alpha to 1 alpha. The value of alpha is small. Therefore, the quadratic equation can be simplified by neglecting alpha in comparison to 1 in the denominator on right-hand side of the equation. Thus, kilobyte is equal to C alpha 2 or alpha is equal to 1.77 times 10⁵ 0.05 is equal to 0.018. O is equal to C alpha is equal to 0.05 times 0.018 is equal to 9.4 times 10⁴ m. H plus is equal to Kw, O is equal to 1014, 9.4 times 10⁴ is equal to 1.06 times 1011. pH is equal to log 1.06 times 1011 is equal to 10.97. Now, using the relation for conjugate acid-base pair, Ka times kilobyte is equal to Kw using the value of kilobyte of NH3 from table 7.7. We can determine the concentration of conjugate acid NH4 plus Ka is equal to Kw kilobyte is equal to 1014. 1.77 times 10⁵ is equal to 5.64 times 1010. 7th November 2006. D and polybasic acids and D and polyacidic bases. Some of the acids like oxalic acid, sulfuric acid and phosphoric acids have more than one ionizable proton per molecule of the acid. Such acids are known as polybasic or polyprotic acids. The ionization reactions, for example for a dibasic acid H2X, are represented by the equations H2X, Ac, H plus, Ac, plus HX, Ac, HX, Ac, H plus, Ac, plus X2, Ac, and the corresponding equilibrium constants are given below. K1 is equal to H plus, HX, H2X, and 2019 to 20. 224 Chemistry. K2 is equal to H plus, X2, HX dash. Here, K1 and K2 are called the first and second ionization constants respectively of the acid H2X. Similarly, for tribasic acids like H3PO4 we have three ionization constants. The values of the ionization constants for some common polyprotic acids are given in table 7.8. In general, when strength of HA bond decreases, that is, the energy required to break the bond decreases, Ha becomes a stronger acid. Also, when the HA bond becomes more polar, i.e., the electronegativity difference between the atoms H and A increases and there is marked charge separation, cleavage of the bond becomes easier, thereby increasing the acidity. But it should be noted that while comparing elements in the same group of the periodic table, HA bond strength is a more important factor in determining acidity than its polar nature. As the size of A increases down the group, HA bond strength decreases and so the acid strength increases. For example, size increases HF, HCl, HBr, high acid strength increases. Similarly, H2S is stronger acid than H2O. But, when we discuss elements in the same row of the periodic table, HA bond polarity becomes the deciding factor for determining the acid strength. As the electronegativity of A increases, the strength of the acid also increases. For example, electronegativity of A increases CH4, NH3, H2O, HF acid strength increases. 7th November 2008 Common ion effect in the ionization of acids and bases. Consider an example of acetic acid dissociation equilibrium represented as CH3Cu, Ac, H plus, Ac, plus CH3Cu, Ac, or HAC, Ac, H plus, Ac, plus AC, Ac. Ka is equal to H plus, AC, HAC. Addition of acetate ions to an acetic acid solution results in decreasing the concentration of hydrogen ions, H plus. Also, if H plus ions are added from an external source, then the equilibrium moves in the direction of undissociated acetic acid, i.e., in a direction of reducing the concentration of hydrogen ions, H plus. This phenomenon is an example of Table 7.8. The ionization constants of some common polyprotic acids, 298 K. It can be seen that higher order ionization constants, K2, K3, are smaller than the lower order ionization constant, K1, of a polyprotic acid. The reason for this is that it is more difficult to remove a positively charged proton from a negative ion due to electrostatic forces. This can be seen in the case of removing a proton from the uncharged H2CO3 as compared from a negatively charged HCO3. Similarly, it is more difficult to remove a proton from a doubly charged HPO42 anion as compared to H2PO4. Polyprotic acid solutions contain a mixture of acids like H2A, Ha and A2 in case of a diprotic acid. H2A being a strong acid, the primary reaction involves the dissociation of H2A, and H3O+ in the solution comes mainly from the first dissociation step. 7th November 2007. Factors affecting acid strength. Having discussed quantitatively the strengths of acids and bases, we come to a stage where we can calculate the pH of a given acid solution. But the curiosity rises about why should some acids be stronger than others? What factors are responsible for making them stronger? The answer lies in its being a complex phenomenon. But, broadly speaking, we can say that the extent of dissociation of an acid depends on the strength and polarity of the HA bond. 2019-20. Double 2,5 equilibrium common ion effect. It can be defined as a shift in equilibrium on adding a substance that provides more of an ionic species already present in the dissociation equilibrium. Thus, we can say that common ion effect is a phenomenon based on the Le Chatelier's principle discussed in section 7.8. In order to evaluate the pH of the solution resulting on addition of 0.05 m acetate ion to 0.05 m acetic acid solution, we shall consider the acetic acid dissociation equilibrium once again, HAC, AC, H plus, AC, plus AC, AC, initial concentration, M, 0.0500.05. Let X be the extent of ionization of acetic acid. Change in concentration, M, X plus X plus X. Equilibrium concentration, M, 0.05 X X 0.05 plus X. Therefore, K is equal to H plus AC, HAC is equal to 0.05 plus X. Kiss smiley, 0.05x, as K is small for a very weak acid, X, 0.05. Hence, 0.05 plus kiss smiley, 0.05 kiss smiley 0.05. Thus, 1.8 times 10⁵ is equal to, kiss smiley, 0.05 plus kiss smiley, 0.05 kiss smiley is equal to X, 0.05, 0.05, is equal to X is equal to, H plus, is equal to 1.8 times 10⁵ mph is equal to log, 1.8 times 10⁵, is equal to 4.74. Problem 7.24. Calculate the pH of a 0.10 m ammonia solution. Calculate the pH after 50.0 ml of this solution is treated with 25.0 ml of 0.10 mHCl. The dissociation constant of ammonia, kilobyte, is equal to 1.77 times 10⁵ solution NH3 plus H2O NH4 plus O. Kilobyte is equal to NH4 plus O NH3 is equal to 1.77 times 10⁵ before neutralization. NH4 plus is equal to O is equal to X, NH3 is equal to 0.10 x 0.10 x 2/0.10 is equal to 1.77 times 10^5. Thus, x is equal to 1.33 times 10^3 is equal to O. Therefore, H plus is equal to Kw, O is equal to 1014, 1.33 times 10^3 is equal to 7.51 times 1012. pH is equal to log 7.5 times 1012 is equal to 11.12 on addition of 25 ml of 0.1 m HCl solution, i.e., 2.5 mole of HCl, to 50 ml of 0.1 m ammonia solution, i.e., 5 mole of NH3, 2.5 mole of ammonia molecules are neutralized. The resulting 75 ml solution contains the remaining unneutralized 2.5 mole of NH3 molecules and 2.5 mole of NH4+. NH3 plus HCl NH4 plus Cl 2.5 at equilibrium 2.5. The resulting 75 ml of solution contains 2.5 mole of NH4 plus ions, i.e., 0.033 m, and 2.5 mole, i.e., 0.033 m, of unneutralized NH3 molecules. This NH3 exists in the following equilibrium: NH4O NH4 plus O 0.033 MYYY, where Y is equal to O is equal to NH4 plus. The final 75 ml solution after neutralization already contains 2.5 mmol NH4 plus ions, i.e. 0.033 m. Thus total concentration of NH4 plus ions is given as NH4 plus is equal to 0.033 plus Y, as Y is small, NH4O 0.033 m and NH4 plus 0.033 m. We know kilobyte is equal to NH4 plus O. NH4O is equal to Y 0.033. 0.033 is equal to 1.77 times 10^5 m. Thus, Y is equal to 1.77 times 10^5 is equal to O. H plus is equal to 1014. 1.77 times 10^5 is equal to 0.56 times 10^9. Hence, pH is equal to 9.24. 7th November 2009. Hydrolysis of salts and the pH of their solutions. Salts formed by the reactions between acids and bases in definite proportions undergo ionization in water. The cations anions formed 2019-20. Chemistry on ionization of salts either exist as hydrated ions in aqueous solutions or interact with water to reform corresponding acids bases depending upon the nature of salts. The later process of interaction between water and cations anions or both of salts is called hydrolysis. The pH of the solution gets affected by this interaction. The cations, e.g., Na plus, K plus, Ca2 plus, Ba2 plus, etc., of strong bases and anions, e.g., Cl, Br, number 3, close O4, etc., of strong acids simply get hydrated but do not hydrolyze, and therefore the solutions of salts formed from strong acids and bases are neutral, i.e., their pH is 7. However, the other category of salts do undergo hydrolysis. We now consider the hydrolysis of the salts of the following types: I. Salts of weak acid and strong base, e.g., CH3CONA. 2. Salts of strong acid and weak base, e.g., NH4Cl. And 3. Salts of weak acid and weak base, e.g., CH3CON4. In the first case, CH3CONA being a salt of weak acid, CH3Co and strong base, now H gets completely ionized in aqueous solution. CH3CONA, AC, CH3Co, AC, plus Na plus, AC, acetate ion thus formed undergoes hydrolysis in water to give acetic acid and O ions CH3Co, AC, plus H2O, L, CH3Co, AC, plus O, AC, acetic acid being a weak acid, Ca is equal to 1.8 times 10⁵, remains mainly unionized in solution. This results in increase of O ion concentration in solution, making it alkaline. The pH of such a solution is more than 7. Similarly, NH4Cl formed from weak base, NH4O and strong acid, HCl, in water dissociates completely. NH4Cl, AC, NH plus 4, AC, plus Cl, AC. Ammonium ions undergo hydrolysis with water to form NH4O and H plus ions NH plus 4, AC, plus H2O, 1, NH4O, AC, plus H plus, AC. Ammonium hydroxide is a weak base. Kilobyte is equal to 1.77 times 10⁵, and therefore remains almost unionized in solution. This results in increased of H plus ion concentration in solution, making the solution acidic. Thus, the pH of NH4Cl solution in water is less than 7. Consider the hydrolysis of CH3CON4 salt formed from weak acid and weak base. The ions formed undergo hydrolysis as follow: CH3Co plus NH4 plus H2O, CH3Co plus NH4O, CH3Co and NH4O also remain into partially dissociated form. CH3Co plus H plus NH4O, NH4 plus OH2OH plus O. Without going into detailed calculation, it can be said that degree of hydrolysis is independent of concentration of solution, and pH of such solutions is determined by their pK values. pH is equal to 7 plus a half. pK per kilobyte, 7.38. The pH of solution can be greater than 7, if the difference is positive, and it will be less than 7, if the difference is negative. Problem 7.25. The pK of acetic acid and p kilobyte of ammonium hydroxide are 4.76 and 4.75 respectively. Calculate the pH of ammonium acetate solution. Solution pH is equal to 7 plus a half. pK per kilobyte is equal to 7 plus a half. 4.76 4.75 is equal to 7 plus a half. 0.01 is equal to 7 plus 0.005 is equal to 7.005. 7.12 Buffer solutions. Many body fluids, e.g., blood or urine, have definite pH, and any deviation in their pH indicates malfunctioning of the body. The control of pH is also very important in many chemical and biochemical processes. Many medical and cosmetic formulations require that these be kept and administered at a particular pH. The solutions which resist change in pH on dilution or with the addition of small amounts of acid or alkali are called buffer solutions. Buffer solutions 2019-20. 227 Equilibrium of known pH can be prepared from the knowledge of pK of the acid or p kilobyte of base, and by controlling the ratio of the salt and acid or salt and base. A mixture of acetic acid and sodium acetate acts as buffer solution around pH 4.75, and a mixture of ammonium chloride and ammonium hydroxide acts as a buffer around pH 9.25. You will learn more about buffer solutions in higher classes. 7th December 2001 Designing buffer solution. Knowledge of pK. p kilobyte and equilibrium constant help us to prepare the buffer solution of known pH? Let us see how we can do this. Preparation of acidic buffer. To prepare a buffer of acidic pH, we use weak acid and its salt formed with strong base. We develop the equation relating the pH, the equilibrium constant, Ka of weak acid and ratio of concentration of weak acid and its conjugate base. For the general case where the weak acid Ha ionizes in water, Ha plus H2O H3O plus A, for which we can write the expression rearranging the expression we have, taking logarithm on both the sides and rearranging the terms we get, or 7.39, 7.40, the expression 7.40 is known as Henderson-Hasselbalch equation. The quantity is the ratio of concentration of conjugate base, anion, of the acid and the acid present in the mixture. Since acid is a weak acid, it ionizes to a very little extent and concentration of Ha is negligibly different from concentration of acid taken to form buffer. Also, most of the conjugate base, A, comes from the ionization of salt of the acid. Therefore, the concentration of conjugate base will be negligibly different from the concentration of salt. Thus, equation 7.40 takes the form ppKH is equal to salt, acid, plus log in the equation 7.39. If the concentration of A is equal to the concentration of Ha, then pH is equal to pK because value of log 1 is 0. Thus if we take molar concentration of acid and salt, conjugate base, same, the pH of the buffer solution will be equal to the pK of the acid. So for preparing the buffer solution of the required pH, we select that acid whose pK is close to the required pH. For acetic acid, pK value is 4.76, therefore pH of the buffer solution formed by acetic acid and sodium acetate taken in equal molar concentration will be around 4.76. A similar analysis of a buffer made with a weak base and its conjugate acid leads to the result, pOH is equal to P plus log, conjugate acid BH plus, base B, BK, 7.41. pH of the buffer solution can be calculated by using the equation pH plus pOH is equal to 14. We know that pH plus pOH is equal to pKW and pK plus p kilobyte is equal to pKW. On putting these values in equation 7.41, it takes the form as follows: pH is equal to pp, conjugate acid BH, base B, WWKKKA plus log, or pH is equal to P, conjugate acid BH, base B, K plus log, 7.42. If molar concentration of base and its conjugate acid, cation, is same, then pH of the buffer solution will be same as pK for the base. pK value for ammonia is 9.25. Therefore a buffer of pH close to 9.25 can be obtained by taking ammonia solution and ammonium 2019 to 20. (228) Chemistry: chloride solution of same molar concentration. For a buffer solution formed by ammonium chloride and ammonium hydroxide, equation 7.42 becomes pH is equal to conjugate acid BH, base B, 9.25 log plus pH of the buffer solution is not affected by dilution because ratio under the logarithmic term remains unchanged. 7.13 Solubility: equilibria of sparingly soluble salts. We have already known that the solubility of ionic solids in water varies a great deal. Some of these, like calcium chloride, are so soluble that they are hygroscopic in nature and even absorb water vapor from atmosphere. Others, such as lithium fluoride, have so little solubility that they are commonly termed as insoluble. The solubility depends on a number of factors, important amongst which are the lattice enthalpy of the salt and the solvation enthalpy of the ions in a solution. For a salt to dissolve in a solvent, the strong forces of attraction between its ions, lattice enthalpy, must be overcome by the ion-solvent interactions. The solvation enthalpy of ions is referred to in terms of solvation, which is always negative, i.e. energy is released in the process of solvation. The amount of solvation enthalpy depends on the nature of the solvent. In case of a nonpolar, covalent solvent, solvation enthalpy is small and hence not sufficient to overcome lattice enthalpy of the salt. Consequently, the salt does not dissolve in nonpolar solvent. As a general rule, for a salt to be able to dissolve in a particular solvent, its solvation enthalpy must be greater than its lattice enthalpy so that the latter may be overcome by former. Each salt has its characteristic solubility which depends on temperature. We classify salts on the basis of their solubility in the following three categories. Category I, soluble solubility, 0.1 m. Category 2, slightly 0.01 m. Solubility, 0.1 m. Soluble. Category 3, sparingly solubility, 0.01 m. Soluble. We shall now consider the equilibrium between the sparingly soluble ionic salt and its saturated aqueous solution. 7.13.1 Solubility product constant. Let us now have a solid like barium sulfate in contact with its saturated aqueous solution. The equilibrium between the undissolved solid and the ions in a saturated solution can be represented by the equation BaSO4 S Ba2 plus Ac plus SO42 Ac. The equilibrium constant is given by the equation K is equal to Ba2 plus SO42 BaSO4. For a pure solid substance, the concentration remains constant and we can write Ksp is equal to K BaSO4 is equal to Ba2 plus SO42 7.43. We call Ksp the solubility product constant or simply solubility product. The experimental value of Ksp in above equation at 298 K is 1.1 times 1010. This means that for solid barium sulfate in equilibrium with its saturated solution, the product of the concentrations of barium and sulfate ions is equal to its solubility product constant. The concentrations of the two ions will be equal to the molar solubility of the barium sulfate. If molar solubility is S, then 1.1 times 1010 is equal to S is equal to S2 or S is equal to 1.05 times 10^5. Thus, molar solubility of barium sulfate will be equal to 1.05 times 10^5 mol L1. A salt may give on dissociation two or more than two anions and cations carrying different charges. For example, consider a salt like zirconium phosphate of molecular formula Zr4 plus 3, PO43, 4. It dissociates into 3 zirconium cations of charge plus 4 and 4 phosphate anions of charge 3. If the molar solubility of zirconium phosphate is S, then it can be seen from the stoichiometry of the compound that Zr4 plus is equal to 3S and PO43 is equal to 4S and Ksp is equal to 3S, 3, 4S, 4 is equal to 6912, S, 7 or S is equal to Ksp, 33 times 44, 17 is equal to Ksp 6912, 17 2019 to 20. 229 Equilibrium, a solid salt of the general formula MXXPyQ plus with molar solubility S in equilibrium with its saturated solution may be represented by the equation MXXY S XMP plus AC plus YXQ AC, where X times P plus is equal to Y times Q, and its solubility product constant is given by Ksp is equal to Mp plus X, Xq, Y is equal to Xs, X, Ys, Y, 7.44, is equal to XX, YY, S, X plus Y, S, X plus Y, is equal to Ksp XX, YYS is equal to Ksp XXYY, 1x plus Y, 7.45. The term Ksp in equation is given by QSP, section 7th June 2002, when the concentration of one or more species is not the concentration under equilibrium. Obviously under equilibrium conditions Ksp is equal to Qsp, but otherwise it gives the direction of the processes of precipitation or dissolution. The solubility product constants of a number of common salts at 298 K are given in Table 7.9. Table 7.9. The solubility product constants, Ksp of some common ionic salts at 298 K. Problem 7.26. Calculate the solubility of A2X3 in pure water, assuming that neither kind of ion reacts with water. The solubility product of A2X3, Ksp is equal to 1.1 times 1023. Solution A2X3 to A3 plus 3x2 Ksp is equal to A3 plus 2 x2. 3 is equal to 1.1 times 1023. If S is equal to solubility of A2X3, then A3 plus is equal to 2S, x2 is equal to 3S. Therefore, Ksp is equal to 2S, 2, 3S, 3 is equal to 108 S5 is equal to 1.1 times 1023. Thus, S5 is equal to 1 times 1025. S is equal to 1.0 times 105 mol L. Problem 7.27. The values of Ksp of two sparingly soluble salts NeO2 and AgCN are 2.0 times 1015 and 6 times 017 respectively. Which salt is more soluble? Explain. Solution AgCN Ag++ Cn 2019 to 20. (230) Chemistry. Ksp is equal to Ag plus Cn is equal to 6 times 1017 NeO2 Ne2 plus 2O. Ksp is equal to Ne2 plus O2 is equal to 2 times 1015. Let Ag plus is equal to S1, then Cn dash is equal to S1. Let Ne2 plus is equal to S2, then O is equal to 2S2. S12 is equal to 6 times 1017. S1 is equal to 7.8 times 109. S2, 2S2, 2 is equal to 2 times 1015. S2 is equal to 0.58 times 104. Ne2 is more soluble than AgCN. 7.13.2 Common ion effect on solubility of ionic salts. It is expected from Le Chatelier's principle that if we increase the concentration of any one of the ions, it should combine with the ion of its opposite charge and some of the salt will be precipitated till once again Ksp is equal to Qsp. Similarly, if the concentration of one of the ions is decreased, more salt will dissolve to increase the concentration of both the ions till once again Ksp is equal to Qsp. This is applicable even to soluble salts like sodium chloride, except that due to higher concentrations of the ions, We use their activities instead of their molarities in the expression for QsP. Thus if we take a saturated solution of sodium chloride and pass HCl gas through it, then sodium chloride is precipitated due to increased concentration, activity, of chloride ion available from the dissociation of HCl. Sodium chloride thus obtained is of very high purity, and we can get rid of impurities like sodium and magnesium sulfates. The common ion effect is also used for almost complete precipitation of a particular ion as its sparingly soluble salt, with very low value of solubility product for gravimetric estimation. Thus we can precipitate silver ion as silver chloride, ferric ion as its hydroxide, or hydrated ferric oxide, and barium ion as its sulfate for quantitative estimations. Dissolution of S-mol L of Ne(O)2 provides S-mol L of Ne2 plus and 2 S-mol L of O, but the total concentration of O is equal to 0.10 plus 2 S-mol L because the solution already contains 0.10 mol L of O from now H. Ksp is equal to 2.0 times 1015 is equal to Ne2 plus O2 is equal to S 0.10 plus 2S, 2 as Ksp is small, 2S 0.10, thus 0.10 plus 2S 0.10, hence 2.0 times 1015 is equal to S 0.10. 2S is equal to 2.0 times 1013 m is equal to Ne2 plus. The solubility of salts of weak acids like phosphates increases at lower pH. This is because at lower pH the concentration of the anion decreases due to its protonation. This in turn increases the solubility of the salt so that Ksp is equal to Qsp. We have to satisfy two equilibria simultaneously, i.e., Ksp is equal to m plus x, Hx is equal to Ka, H plus, taking inverse of both side and adding 1 we get HxxHxHxHaa plus is equal to plus is equal to plus 11 kkk. Now, again taking inverse, we get x plus Hx is equal to F is equal to Ka plus H plus, and it can be seen that F decreases as pH decreases. If S is the solubility of the salt at a given pH, then Ksp is equal to S. Fs is equal to S2 Ka plus H plus, and S is equal to Ksp H plus Ka 1 to 7.46. Thus solubility S increases with increase in H plus or decrease in pH. Problem 7.28 calculate the molar solubility of Ne(O)2 in 0.10 m. Now H. The ionic product of Ne(O)2 is 2.0 times 1015. Solution let the solubility of Ne(O)2 be equal to S 2019 to 20. 231 Equilibrium summary. When the number of molecules leaving the liquid to vapor equals the number of molecules returning to the liquid from vapor, equilibrium is said to be attained and is dynamic in nature. Equilibrium can be established for both physical and chemical processes, and at this stage rate of forward and reverse reactions are equal. Equilibrium constant Kc is expressed as the concentration of products divided by reactants, each term raised to the stoichiometric coefficient. For reaction, A plus B C plus D Kc is equal to C D A B. Equilibrium constant has constant value at a fixed temperature, and at this stage all the macroscopic properties such as concentration, pressure, etc. become constant. For a gaseous reaction, equilibrium constant is expressed as Kp and is written by replacing concentration terms by partial pressures in Kc expression. The direction of reaction can be predicted by reaction quotient Qc, which is equal to Kc at equilibrium. Le Chatelier's principle states that the change in any factors such as temperature, pressure, concentration, etc. will cause the equilibrium to shift in such a direction so as to reduce or counteract the effect of the change. It can be used to study the effect of various factors such as temperature, concentration, pressure, catalyst and inert gases on the direction of equilibrium and to control the yield of products by controlling these factors. Catalyst does not affect the equilibrium composition of a reaction mixture but increases the rate of chemical reaction by making available a new lower energy pathway for conversion of reactants to products and vice versa. All substances that conduct electricity in aqueous solutions are called electrolytes. Acids, bases and salts are electrolytes, and the conduction of electricity by their aqueous solutions is due to anions and cations produced by the dissociation or ionization of electrolytes in aqueous solution. The strong electrolytes are completely dissociated. In weak electrolytes there is equilibrium between the ions and the unionized electrolyte molecules. According to Arrhenius, acids give hydrogen ions while bases produce hydroxyl ions in their aqueous solutions. Bronsted-Lowry, on the other hand, defined an acid as a proton donor and a base as a proton acceptor. When a Bronsted-Lowry acid reacts with a base, it produces its conjugate base and a conjugate acid corresponding to the base with which it reacts. Thus a conjugate pair of acid-base differs only by one proton. Lewis further generalized the definition of an acid as an electron pair acceptor and a base as an electron pair donor. The expressions for ionization, equilibrium, constants of weak acids, Ka, and weak bases, kilobyte, are developed using Arrhenius definition. The degree of ionization and its dependence on concentration and common ion are discussed. The pH scale, pH is equal to log H+, for the hydrogen ion concentration, activity, has been introduced and extended to other quantities. pOH is equal to log O, pK is equal to log Ka, p kilobyte is equal to log kilobyte, and pKw is equal to log kW, etc. The ionization of water has been considered, and we note that the equation pH plus pOH is equal to pKw is always satisfied. The salts of strong acid and weak base, weak acid and strong base, and weak acid and weak base undergo hydrolysis in aqueous solution. The definition of buffer solutions and their importance are discussed briefly. The solubility equilibrium of sparingly soluble salts is discussed, and the equilibrium constant is introduced as solubility product constant, Ksp. Its relationship with solubility of the salt is established. The conditions of precipitation of the salt from their solutions or their dissolution in water are worked out. The role of common ion and the solubility of sparingly soluble salts is also discussed. 2019-20. 232 Chemistry suggested activities for students regarding this unit. The student may use pH paper in determining the pH of fresh juices of various vegetables and fruits, soft drinks, body fluids, and also that of water samples available. B. The pH paper may also be used to determine the pH of different salt solutions, and from that he/she may determine if these are formed from strong weak acids and bases. C. They may prepare some buffer solutions by mixing the solutions of sodium acetate and acetic acid and determine their pH using pH paper. D. They may be provided with different indicators to observe their colors in solutions of varying pH. E. They may perform some acid-base titrations using indicators. F. They may observe common ion effect on the solubility of sparingly soluble salts. G. If pH meter is available in their school, they may measure the pH with it and compare the results obtained with that of the pH paper. Exercises 7.1 A liquid is in equilibrium with its vapor in a sealed container at a fixed temperature. The volume of the container is suddenly increased. A. What is the initial effect of the change on vapor pressure? B. How do rates of evaporation and condensation change initially? C. What happens when equilibrium is restored finally and what will be the final vapor pressure? 7.2 What is Kc for the following equilibrium when the equilibrium concentration of each substance is SO2 is equal to 0.60 m, O2 is equal to 0.82 m and SO3 is equal to 1.90 m. 2 SO2 G plus O2 G 2 SO3 G 7.3 at a certain temperature and total pressure of 105 Pa. Iodine vapor contains 40% by volume of I atoms I2 G 2I G. Calculate Kp for the equilibrium. 7.4 Write the expression for the equilibrium constant, Kc for each of the following reactions, I, 2NOCl, G, 2NO, G, plus Cl2, G, 2, 2Cu, number 3, 2, S, 2Co, S, plus 4NO2, G, plus O2, G, 3, CH3Cu2H5, Ac, plus H2O, L, CH3Cu, Ac, plus C2H5O, Ac, 4, Fe3 plus, Ac, plus 3O, Ac, Fe, O, 3, S, V, I2, S, plus 5F22 if 7.5 Find out the value of Kc for each of the following equilibria from the value of Kp, I, 2NOCl, G, 2NO, G, plus Cl2, G. Kp is equal to 1.8 times 10 to at 500 K. 2. CaCO3, S, CaO, S, plus Co2, G. Kp is equal to 167 at 1073 K. 7.6 For the following equilibrium, Kc is equal to 6.3 times 1014 at 1000 K. No, G, plus O3, G, number 2, G, plus O2, G. Both the forward and reverse reactions in the equilibrium are elementary bimolecular reactions. What is Kc for the reverse reaction? 2019-20. 233 Equilibrium 7.7 Explain why pure liquids and solids can be ignored while writing the equilibrium constant expression. 7.8 Reaction between N2 and O2 takes place as follows: 2N2, G, plus O2, G, 2N2O, G. If a mixture of 0.482 mol N2 and 0.933 mol of O2 is placed in a 10L reaction vessel and allowed to form N2O at a temperature for which Kc is equal to 2.0 times 1037, determine the composition of equilibrium mixture. 7.9 Nitric oxide reacts with Br2 and gives nitrosyl bromide as per reaction given below. 2NO, G, plus Br2, G, 2NOBr, G, when 0.087 mol of NO and 0.0437 mol of Br2 are mixed in a closed container at constant temperature, 0.0518 mol of NOBr is obtained at equilibrium. Calculate equilibrium amount of NO and Br2. 7.10 at 450 kkp is equal to 2.0 times 1010 bar for the given reaction at equilibrium. 2 so 2 G plus O2 G 2 so 3 G. What is Kc at this temperature? 7.11 A sample of high G is placed in flask at a pressure of 0.2 atm. At equilibrium the partial pressure of high G is 0.04 atm. What is Kp for the given equilibrium? 2 high G H2 G plus I2 G. 7.12 A mixture of 1.57 mol of N2, 1.92 mol of H2 and 8.13 mol of NH3 is introduced into a 20L reaction vessel at 500 K. At this temperature, the equilibrium constant, Kc for the reaction N2, G, plus 3H2, G, 2NH3, G, is 1.7 times 102. Is the reaction mixture at equilibrium? If not, what is the direction of the net reaction? 7.13 The equilibrium constant expression for a gas reaction is Kc is equal to NHO no HO3425426. Write the balanced chemical equation corresponding to this expression. 7.141 mole of H2O and 1 mole of Co are taken in 10L vessel and heated to 725 K. At equilibrium 40% of water, by mass, reacts with Co according to the equation, H2O, G, plus Co, G, H2, G, plus Co2, G. Calculate the equilibrium constant for the reaction. 7.15 at 700 K, equilibrium constant for the reaction, H2, G, plus I2, G, 2 high, G, is 54.8. If 0.5 mol L1 of high, G, is present at equilibrium at 700 K, what are the concentration of H2, G, and I2, G? Assuming that we initially started with high G and allowed it to reach equilibrium at 700 K. 7.16 What is the equilibrium concentration of each of the substances in the equilibrium when the initial concentration of ICl was 0.78 m? 2I close G, I2, G, plus Cl2, G. Kc is equal to 0.147.17 Kp is equal to 0.04 atm at 899 K for the equilibrium shown below. What is the equilibrium concentration of C2H6 when it is placed in a flask at 4.0 atm pressure and allowed to come to equilibrium? C2H6, G, C2H4, G, plus H2, G, 2019 to 20. (234) Chemistry 7.18 Ethyl acetate is formed by the reaction between ethanol and acetic acid, and the equilibrium is represented as CH3Cu L plus C2H5O L CH3Cu 2H5 L plus H2O L. I. Write the concentration ratio, reaction quotient, QC. For this reaction, note, water is not in excess and is not a solvent in this reaction. 2. At 293 K, if one starts with 1.00 mol of acetic acid and 0.18 mol of ethanol, there is 0.171 mol of ethyl acetate in the final equilibrium mixture. Calculate the equilibrium constant. 3. Starting with 0.5 mol of ethanol and 1.0 mol of acetic acid and maintaining it at 293 K, 0.214 mol of ethyl acetate is found after some time. Has equilibrium been reached? 7.19 A sample of pure PCl5 was introduced into an evacuated vessel at 473 K. After equilibrium was attained, concentration of PCl5 was found to be 0.5 times 10⁻⁻³ mol L1. If value of Kc is 8.3 times 10⁻⁻³, what are the concentrations of PCl3 and Cl2 at equilibrium? PCl5, G, PCl3, G, plus Cl2, G. 7.201 of the reaction that takes place in producing steel from iron ore is the reduction of iron, 2, oxide by carbon monoxide to give iron metal and Co2. FeO, S, plus Co, G, Fe, S, plus Co2, G. Kp is equal to 0.265 atm at 1050 K. What are the equilibrium partial pressures of Co and Co2 at 1050 K if the initial partial pressures are PCO is equal to 1.4 atm and is equal to 0.80 atm. 7.21 Equilibrium constant, Kc for the reaction N2, G, plus 3H2, G. 2NH3, G, at 500 K is 0.061 at a particular time. The analysis shows that composition of the reaction mixture is 3.0 mol L1 N2, 2.0 mol L1 H2 and 0.5 mol L1 NH3. Is the reaction at equilibrium? If not, in which direction does the reaction tend to proceed to reach equilibrium? 7.22 Bromine monochloride, BrCl decomposes into bromine and chlorine and reaches the equilibrium, 2 BrCl, G, Br2, G, plus Cl2, G, for which Kc is equal to 32 at 500 K. If initially pure BrCl is present at a concentration of 3.3 times 10⁻³ mol L1, what is its molar concentration in the mixture at equilibrium? 7.23 at 1127 K and 1 atm pressure, a gaseous mixture of Co and Co2 in equilibrium with soiled carbon has 90.55% Co by mass C, S, plus Co2, G, 2 Co, G. Calculate Kc for this reaction at the above temperature. 7.24 Calculate A, G and B, the equilibrium constant for the formation of number 2 from NO and O2 at 298 K NO, G, plus a half O2, G, number 2, G, where Fg, number 2, is equal to 52.0 kJ mol Fg, NO, is equal to 87.0 kJ mol Fg, O2, is equal to 0 kJ mol 7.25. Does the number of moles of reaction products increase, decrease or remain same when each of the following equilibria is subjected to a decrease in pressure by increasing the volume? A. PCl5, G, PCl3, G, plus Cl2, G. 2019-20. 235 Equilibrium, B, CaO, S, plus Co2, G, CaCO3, S, C, 3 Fe, S, plus 4H2O, G, Fe3O4, S, plus 4H2, G. 7.26 Which of the following reactions will get affected by increasing the pressure? Also, mention whether change will cause the reaction to go into forward or backward direction. I, COCl2, G, Co, G, plus Cl2, G, 2, CH4, G, plus 2S2, G, CS2, G, plus 2H2S, G, 3, Co2, G, plus C, S, 2 Co, G, 4, 2H2, G, plus Co, G, CH3O, G, V, CaCO3, S, CaO, S, plus Co2, G, 6, 4NH3, G, plus 5O2, G, 4 No, G, plus 6H2O, G, 7.27. The equilibrium constant for the following reaction is 1.6 times 105 at 1024 kH2, G, plus Br2, G, 2HBr, G. Find the equilibrium pressure of all gases if 10.0 bar of HBr is introduced into a sealed container at 1024 K. 7.28. The hydrogen gas is obtained from natural gas by partial oxidation with steam as per following endothermic reaction: CH4, G, plus H2O, G, Co, G, plus 3H2, G, A. Write as expression for Kp for the above reaction. B. How will the values of Kp and composition of equilibrium mixture be affected by I. Increasing the pressure, 2. Increasing the temperature, 3. Using a catalyst. 7.29. Describe the effect of A. Addition of H2B, addition of CH3OC, removal of CO-D, removal of CH3O on the equilibrium of the reaction: 2H2, G, plus CO, G, CH3O, G. 7.30 at 473 K. Equilibrium constant Kc for decomposition of phosphorus pentachloride, PCl5 is 8.3 times 10-3. If decomposition is depicted as PCl5, G, PCl3, G, plus Cl2, G, RH is equal to 124.0 kJ mol 1A. Write an expression for Kc for the reaction. B. What is the value of Kc for the reverse reaction at the same temperature? C. What would be the effect on Kc if I. more PCl5 is added, 2. Pressure is increased, 3. The temperature is increased. 7.31. The hydrogen gas used in Haber's process is produced by reacting methane from natural gas with high temperature steam. The first stage of two-stage reaction involves the formation of CO and H2. In second stage, CO formed in first stage is reacted with more steam in water-gas shift reaction: CO, G, plus H2O, G, CO2, G, plus H2, G, 2019-20. 236. Chemistry. If a reaction vessel at 400 degrees Celsius is charged with an equimolar mixture of CO and steam such that PCO is equal to pH2O is equal to 4.0 bar, what will be the partial pressure of H2 at equilibrium? Kp is equal to 10.1 at 400 degrees Celsius. 7.32. Predict which of the following reaction will have appreciable concentration of reactants and products: A. Cl2, G, 2Cl, G. Kc is equal to 5 times 1039. B. Cl2, G, plus 2 No, G, 2NOCl, G. Kc is equal to 3.7 times 108 C, Cl2, G, plus 2 No2, G, 2 No2Cl, G. Kc is equal to 1.87.33. The value of Kc for the reaction 3O2, G, 2O3, G, is 2.0 times 1050 at 25 degrees Celsius. If the equilibrium concentration of O2 in air at 25 degrees Celsius is 1.6 times 10^2, what is the concentration of O3? 7.34. The reaction CO, G, plus 3H2, G, CH4, G, plus H2O, G, is at equilibrium at 1300 K in a 1L flask. It also contains 0.30 mol of CO, 0.10 mol of H2 and 0.02 mol of H2O and an unknown amount of CH4 in the flask. Determine the concentration of CH4 in the mixture. The equilibrium constant, Kc for the reaction at the given temperature is 3.90. 7.35 What is meant by the conjugate acid-base pair? Find the conjugate acid base for the following species: HNO2, CN, HLO4, FO, CO32, and S2. 7.36 Which of the followings are Lewis acids? H2O, BF3, H+, and NH4+. 7.37 What will be the conjugate basis for the Bronsted acids? HF, H2SO4, and HCO3. 7.38 Write the conjugate acids for the following Bronsted bases: NH2, NH3, and HCO. 7.39 The species: H2O, HCO3, HSO4, and NH3 can act both as Bronsted acids and bases. For each case give the corresponding conjugate acid and base. 7.40 Classify the following species into Lewis acids and Lewis bases and show how these act as Lewis acid base: A, O, B, F, C, H+, D, BCl3. 7.41 The concentration of hydrogen ion in a sample of soft drink is 3.8 times 10^3 m. What is its pH? 7.42 The pH of a sample of vinegar is 3.76. Calculate the concentration of hydrogen ion in it. 7.43 The ionization constant of HF, HQ and HCN at 298 K are 6.8 times 10^4, 1.8 times 10^4 and 4.8 times 10^9 respectively. Calculate the ionization constants of the corresponding conjugate base. 7.44 The ionization constant of phenol is 1.0 times 10^10. What is the concentration of phenolate ion in 0.05 m solution of phenol? What will be its degree of ionization if the solution is also 0.01 m in sodium phenolate? 7.45 The first ionization constant of H2S is 9.1 times 10^8. Calculate the concentration of HS ion in its 0.1 m solution. How will this concentration be affected if the solution is 0.1 m in HCl also? If the second dissociation constant of H2S is 1.2 times 10^13, calculate the concentration of S2 under both conditions. 7.46 The ionization constant of acetic acid is 1.74 times 10^5. Calculate the degree of dissociation of acetic acid in its 0.05 m solution. Calculate the concentration of acetate ion in the solution and its pH. 7.47 It has been found that the pH of a 0.01 m solution of an organic acid is 4.15. Calculate the concentration of the anion, the ionization constant of the acid and its pK. 2019-20. 237 Equilibrium 7.48 Assuming complete dissociation, calculate the pH of the following solutions: A. 0.003 m HCl, B. 0.005 m NaOH, C. 0.002 m HBr, D. 0.002 m KOH. 7.49 Calculate the pH of the following solutions: A. 2 g of TLOH dissolved in water to give 2 liter of solution. B. 0.3 g of CaO, 2 dissolved in water to give 500 ml of solution. C. 0.3 g of NaOH dissolved in water to give 200 ml of solution. D. 1 ml of 13.6 m HCl is diluted with water to give 1 liter of solution. 7.50 The degree of ionization of a 0.1 m bromoacetic acid solution is 0.132. Calculate the pH of the solution and the pK of bromoacetic acid. 7.51 The pH of 0.005 m codeine, C18H21NO3, solution is 9.95. Calculate its ionization constant and p kilobyte. 7.52 What is the pH of 0.001 m aniline solution? The ionization constant of aniline can be taken from table 7.7. Calculate the degree of ionization of aniline in the solution. Also calculate the ionization constant of the conjugate acid of aniline. 7.53 Calculate the degree of ionization of 0.05 m acetic acid if its pK value is 4.74. How is the degree of dissociation affected when its solution also contains a. 0.01 m, b. 0.1 m in HCl? 7.54 The ionization constant of dimethylamine is 5.4 times 10⁴. Calculate its degree of ionization in its 0.02 m solution. What percentage of dimethylamine is ionized if the solution is also 0.1 m in NaOH? 7.55 Calculate the hydrogen ion concentration in the following biological fluids whose pH are given below. A. Human muscle fluid, 6.83, b. Human stomach fluid, 1.2, c. Human blood, 7.38, d. Human saliva, 6.4. 7.56 The pH of milk, black coffee, tomato juice, lemon juice and egg white are 6.8, 5.0, 4.2, 2.2 and 7.8 respectively. Calculate corresponding hydrogen ion concentration in each. 7.57 If 0.561 g of KOH is dissolved in water to give 200 ml of solution at 298 K, calculate the concentrations of potassium, hydrogen and hydroxyl ions. What is its pH? 7.58 The solubility of senior O2 at 298 K is 19.23 gl of solution. Calculate the concentrations of strontium and hydroxyl ions and the pH of the solution. 7.59 The ionization constant of propanoic acid is 1.32 times 10⁵. Calculate the degree of ionization of the acid in its 0.05 m solution and also its pH. What will be its degree of ionization if the solution is 0.01 m in HCl also? 7.60 The pH of 0.1 m solution of cyanic acid, HCNO, is 2.34. Calculate the ionization constant of the acid and its degree of ionization in the solution. 7.61 The ionization constant of nitrous acid is 4.5 times 10⁴. Calculate the pH of 0.04 m sodium nitrite solution and also its degree of hydrolysis. 7.62 A 0.02 m solution of pyridinium hydrochloride has pH is equal to 3.44. Calculate the ionization constant of pyridine. 7.63 Predict if the solutions of the following salts are neutral, acidic or basic: NaCl, KBr, NaCN, NH4NO3, NaNO2 and Kf. 7.64 The ionization constant of chloroacetic acid is 1.35 times 10⁵. What will be the pH of 0.1 m acid and its 0.1 m sodium salt solution? 2019-20. 238 Chemistry 7.65 Ionic product of water at 310 K is 2.7 times 10⁻14. What is the pH of neutral water at this temperature? 7.66 Calculate the pH of the resultant mixtures. A. 10 ml of 0.2 MCA, O. 2 plus 25 ml of 0.1 MHCl. B. 10 ml of 0.01 MH2 so 4 plus 10 ml of 0.01 MCA, O. 2C. 10 ml of 0.1 MH2 so 4 plus 10 ml of 0.1 MKOH. 7.67 Determine the solubilities of silver chromate, barium chromate, ferric hydroxide, lead chloride and mercurous iodide at 298 K from their solubility product constants given in table 7.9. Determine also the molarities of individual ions. 7.68 The solubility product constant of Ag2-Cro4 and AgBr are 1.1 times 1012 and 5.0 times 1013 respectively. Calculate the ratio of the molarities of their saturated solutions. 7.69 Equal volumes of 0.002 m solutions of sodium iodate and cupric chlorate are mixed together. Will it lead to precipitation of copper iodate? For cupric iodate Ksp is equal to 7.4 times 10^8. 7.70 The ionization constant of benzoic acid is 6.46 times 10^5 and Ksp for silver benzoate is 2.5 times 1013. How many times is silver benzoate more soluble in a buffer of pH 3.19 compared to its solubility in pure water? 7.71 What is the maximum concentration of equimolar solutions of ferrous sulfate and sodium sulfide so that when mixed in equal volumes, there is no precipitation of iron sulfide? For iron sulfide, Ksp is equal to 6.3 times 1018. 7.72 What is the minimum volume of water required to dissolve 1 g of calcium sulfate at 298 K? For calcium sulfate, Ksp is 9.1 times 106. 7.73 The concentration of sulfide ion